also a program chair for this program. And today we have the pleasure to have Pouria for our semantic segmentation workshop. This is our last workshop of the AI Research School, and tomorrow we will have our closing ceremony. So I would just briefly introduce Dr. Pouria Rouzrokh. How do I pronounce your last name correctly?
Yeah, that's very difficult. So it's Rouzrokh in Persian, but basically, yeah, you are fine. Just go with my first name. That's more than me. Yeah, enough.
Rouzrokh. Dr. Pouria Rouzrokh. He's a graduated physician from Tehran University of Medical Sciences, Iran. He's also earned a Master of Public Health and Master of Health Professions education from the same university. He's currently working as a postdoctoral research associate and a scientist at Mayo Clinic, Artificial Intelligence Laboratory, and Orthopedic Surgery, Artificial Intelligence at the Mayo Clinic as well. And he's an aspiring radiologist and loves interdisciplinary studies. Please go ahead. Thank you so much for accepting our invitation to give the workshop today.
Thank you very much, Eugene.
Yeah, feel free to share your screen. Thank you.
Yeah, definitely. Let me just share my screen here and go. So seems that I'm just looking for the share screens. Oh, okay, I found it. All right, so I want to share my entire screen. And you should hopefully now be able to see this, right?
Yes.
Yeah.
Perfect. Awesome. So first of all, hello again to everybody. Hope that you have started a good day. And thank you, Eugene, for your kind words. I am very happy that together we could go through the segmentation workshop today, and hopefully we could learn a couple of things together. But before we start, we need to do a little bit of housekeeping stuff. So the first thing is that we are going to run the codes in Google Collaboratory, but similar to how Bardia managed his session, I believe, I also put together my notebook and a couple of data files that you need for the training in a GitHub repository. So I'm going to put it back in the chat for you so everyone could see that. Please feel free to open it and then follow what I'm doing here on the screen, because that needs a little bit of clicking. That's a very simple process. If you have, if you have already opened any kind of notebook using GitHub, you probably know how it works. But for those of you who have not done that, basically by clicking on that link, you are going to see a web page like that on GitHub. And we are going to work with this notebook here, right? So if you click on that, first, you will see the notebook on GitHub itself, which we basically do not want, right? So we want to play with that somewhere that we could, run the codes ourselves. So there will be a button like this, open in Colab on left top hand side of the notebook. So just click on that, please, and then it will probably open a new tab for you on your browser and bring you to a collaboratory environment. Now, before we proceed, it's important for you to press this copy to drive button again on the top side of the screen. And when you click on that, it will probably duplicate this notebook for you and save that locally somewhere on your Google Drive, right? So basically it seems that for me, the pop-up browsers were blocked. So if that happened for you, just make sure that your browser allows pop-ups to show themselves. And then you will see a new collaboratory notebook like that, right? So these two notebooks are similar, but basically we are going to work with the second one, the one that was created after you clicked on that copy to drive. Because if you wanted to work with this initial version, you would have a lot of difficulties with saving the notebook and sometimes even with running that. So now this notebook, as you see here, the name is copy of notebook. So if you go to your Google Drive, you will find it somewhere either in your root directory or maybe in your Google Collaboratory notebooks. So let me pause here and make sure everybody is following and everybody could do that. Do you have any problems in the process or anything that I can help with? And sorry that I sometimes come back to this screen because I'm running Zoom from my browser and I cannot see your chat and that fancy toolbar on top hand side of the screen. So I basically need to come back here. So hopefully everyone has followed and you are here currently on the notebook, right? And so a couple of things. I have not even started to talk about the workshop itself, but before we start chatting about that, I would like you to do a few introductory things. So we are going to run the few first cells of this notebook. Before we do, the first thing you need to do is that you need to go to this menu, runtime. Click on that, please, and then click on change runtime type. Change runtime type, okay? So this is going to tell Google Collaboratory that you are going to use a GPU for your training, a graphic card, right? So my Google Colab is usually Google Colab Pro. So basically you might see some of these options not available for you, but what you definitely can do is that you can click on this GPU, and then I believe the GPU class will be locked to a standard if you are not on Google Colab Pro, but that's not a problem for 99% of the notebooks. So just make sure that you are actually using GPU here, not the default none option, because that will basically only use the CPU, which we do not like, right? And then when you do so, click on this save button, and you will be back to this main Colab screen. Now, the first lesson, and basically the only thing you need to do today with this workshop is that you need to know how to run different cells in Google Collaboratory. So hopefully most of you have already worked with Colab. If not, you basically have a very easy job ahead of you. You just need to click on either of these cells and press Shift plus Enter. So Shift and Enter on your keyboard at the same time, and you go to the next cell, right? So these are the markdown cells. So basically Google Collaboratory or Jupyter Notebooks in general are these kind of fancy coding environments that lets you to put code and text and images at the same time, as you can see on the screen. So these are some text that I will introduce shortly. But when you come to code cells like this one, you have this play button on the left-hand side, which if you click on that, it will basically run that cell for you. The other shortcut for that, the keyboard shortcut, is as I just mentioned, press Shift and Enter at the same time. And what I want you to do is that just proceed and press Shift and Enter up to this first cell in the data collection. So we want that one to run as well. And then we will pause to just go through the regular introductory stuff. And the reason I did so is that this first cell here that you see is actually downloading the data, cloning that GitHub repository, and things might take 2 or 3 minutes here, so we don't want to waste our time waiting for this download when the actual workshop starts. So again, please come to this Google Collaboratory page, run the first few cells, and make sure that you run everything up to the end of this first cell in the data collection phase, right? So again, if anyone has questions, please feel free to turn on your mic and ask your questions. And I would really appreciate that if you ask questions by basically speaking through your mic rather than typing, because I am not seeing the chat box of Zoom here. So basically, I might miss your question. Or Farhad or Legion, if you just can kindly pause me whenever you thought someone has a question. All right, so if everyone's following, then we probably can talk a little bit about the workshop itself. And before that, so I would like to ask a couple of questions. So I somehow assume that most of the people here have already done some Python programming, PyTorch programming, or even may have trained a classifier. Is that right, Farhad? Hopefully that's a valid assumption. Awesome.
Yes, that's the case.
Awesome, that's great, that's great. So my job then is gonna be much, much easier here. All right, so today we are going to talk about another application in deep learning, which is called semantic segmentation. And before that, I would like you to just note some introductory stuff here. So first of all, whenever we talk about semantic segmentation, we should know what kind of projects we are referring to, right? And I put the definitions for you here. So in a very simplified language, image segmentation is only the task of assigning the label to every pixel in an image, right? So for example, if you look at this dog image here, and if you have trained a model that can segment dogs for you, what it does is that it could basically look at this image and say, hey, I am going to sharply and accurately delineate the boundaries of the dog and all pixels that belong to that on your image, right? So basically, as you would see, in the very final cell of this notebook, you could use segmentation masks to crop the images, for example. So, for example, if you wanted to crop the background and make sure that you're only looking at these dog animal here, you basically could use a segmentation model to very accurately pick the specific object of interest for you and then get rid of the background or any other objects that you do not care about. So that's image segmentation. And you should obviously know what image segmentation, what makes image segmentation different compared to, for example, image classification, in which we only show an image to a model and the model is going to throw out a label for us, like, for example, the dog class, or if it is a cat versus dog classifier, the dog class or a cat class, right? And also an object detection model. So what is an object detection model? That's something that some of you might already have heard about, but an object detection is very much similar to image segmentation in terms of finding an object of interest or maybe an area of interest. But the difference is that whenever you are training an object detection model, you do not care that much about the exact sharp boundaries of your object, right? So you basically just put a bounding box, a rectangular bounding box around that object that you care about. But different than that, in image segmentation, what you do is that you carefully, your model carefully picks whatever pixels that belong to the boundaries of that object and make sure that it's not going to assign any pixel out of that boundary, mistakenly to the dog class, for example. So whenever we are dealing with object detection, we basically are not that much careful about the boundaries. So that's something that you should have in mind. And even though this difference might look like very small, this basically makes the two different tasks of image segmentation and object detection quite different with respect to the amount of time that you need to put on annotating the stuff, right? Because I'm not sure how many of you have already tried to annotate data for training an image segmentation model or training an object detection model. I personally did that a lot, in my first years at Mayo, basically in the first month, say, maybe 2 or 3 months. My only job was to just go through some images and use some software that we had back then to using my mouse, draw these boundaries and then fill them out for training a further segmentation model. And let me tell you, annotating this similar image for training a segmentation model, going through all these boundaries with your mouse is going to be much more tedious compared to the time that you are going to simply just put a rectangle around that, because this doesn't need to be that much accurate. So the take-home message is this. We are going through an image segmentation project for today, and that has a lot of certain use cases. But if you're thinking of an image segmentation project, the first question that you need to ask yourself is that, do you really need an image segmentation project? Or maybe an object detection model can do the job for you? Because that will be game-changing. That will be something that a lot of other people's time would depend on, right? Your time, the annotator's time, and a lot of time, experts' time, because so these are very simple images to annotate, but imagine that you are going through a very complicated CT or MR imaging, and you need to have a radiologist to annotate those images for you. So those people time is costly, and you don't want them to do something that you basically didn't need that much. Maybe if you change your project from an image segmentation to an object detection, you could basically have them annotate more images for you, right? So that's an important thing. And the second question before we proceed is that, what is the difference between semantic segmentation and instance segmentation? Can anyone from the audience turn on their mic and let me know of what they think about this difference between semantic segmentation and instance segmentation? Both are obviously segmentation models, both are deep learning models. What is the difference between the two? What actually makes the significant difference between these two models if you had them? Anyone interested?
You can also type in the chat, and yeah, great. Instance segmentation is much more specific in separation, Anay said.
Yeah, kind of right, Anay, but can you explain a little bit more? What do you mean that it's more specific in separation? And while she's typing, anybody else interested in sharing their opinions?
Yes, in separations means different classes. So
Ishika, it says it does the task at the pixel level. Not quite the answer I was looking for, but thank you for speaking up, because that's something that we need a lot in today's workshop, right? So please, guys, feel free to participate. Feel free to throw out guesses like that. That's not harmful, right? So let's do this together. Instead of me only talking, that's going to be too much boring to you. All right, so seems that no more answers. All right, then I'm going to reveal this one. Oh, here comes NA. Like it's almost like a subset of semantic segmentation. It separates out individual people rather than the whole group of people. Yes, yes, awesome. Yeah, Ishika, now this time it's true. It assigns the unique label to individual object. Thank you to both of you. That was quite right? Now, let me go back to this notebook here. Now, what you're seeing in this screen is that, there is only one dog on these images, right? Now, suppose we had more than one dog, maybe 2 or 3 dogs at the same image. What makes the difference between a semantic segmentation and an instance segmentation model is that a semantic segmentation does not understand the concept of numbers, does not understand that we have 3 dogs. If there were 3 dogs, all of them will be colored blue, like the first one here. So the model would basically assign a total area of dog, right, to some pixels on your image and say, hey, the rest of the pixels are not dog. But if you ask the model, hey, how many dogs did you detect there? It doesn't have any clue about that. But when we deal with an instance segmentation model, it basically is segmenting instances of objects. And as our friends here mentioned, what it does is that if you had 3 dogs there, every dog is gonna be segmented separately. So, if you were somehow overlaying those segmentation masks on the images, for example, every dog would be colored using a different color here, maybe one blue, one red, one green. Now, this makes a huge difference again in the kind of downstream application you have in mind. If you care about basically what kind of if you care about the individual objects in your image, for example, say you are segmenting a blood slice, right? The blood pathology slice. So you have a lot of red blood cells, white blood cells there. You basically care about the numbers of them. Then you basically need an instance segmentation or maybe an object detection, because it also works on, on a basically instance manner. But if you don't care about that, if you only care about the entire area that all objects, regardless of their numbers, occupy, then a semantic segmentation is going to be your choice. Now, for this notebook, we are going to stick to semantic segmentation because that's a little bit easier and, to be honest, even a little bit more applied for you. And we are going to go through that. Now, very quickly, I already talked about the prerequisites. Hopefully you all know about Python and PyTorch programming. The code setup here is a little bit different than what you will usually see in a official real Python project. In a real Python project, we usually have multiple Python files. We still use notebooks for a couple of different things. For example, I personally use notebooks for data cleaning. But it would be very rare if you see an entire project coded in a single notebook. That most of the time doesn't happen, right? At least in very big projects doesn't happen. But today we are going to see everything in a single notebook. So please keep that in mind, that that's a little bit unrealistic. And again, the code in this notebook is not necessarily optimized for performance. It's basically an educational notebook. So you might see a couple of things that have been repeated in different cells. If it was a real project, you basically would like to keep your code as short and concise as possible. Not necessarily the case with me here. And finally, again, for this notebook, I put the majority of the code in the body of the cells. If you're dealing with a regular project, you basically want to have a lot of classes, a lot of functions. You basically don't want to run the code in the middle of the Python script or Jupyter notebook, but let's take it easy. We are doing that now. All right, so with those housekeeping stuff in mind, we are going to start the notebook and go through what we need to do. The first thing here is that we are going to use a library called Monai a lot for many of the things that we are going to do today. And Monai is something that is not already installed on Google Colab, so you basically need to install it. I basically usually work with this version of Mona. I keep an eye on new versions, but do not necessarily update my package unless I find something fancy that is going to help me a lot. So this is not a very old version. This is basically a recent one, but probably not the most recent one. But anyway, so as far as the code was working with this version, I keep it here. You are going to install that in Google Colab, and then we are going to, import a couple of packages here, which we are going to use further down the line. And then this cell here, I'm not going to explain it in detail because that's just housekeeping. What we did was that we cloned the repository we started with, put it in the Google Colab document, folder organization, and then just cleaned the stuff a little bit to make sure that the rest of the notebook works fine. And finally, in the last cell we ran together, we unzipped the data set we had. Now, speaking of the data set and the task, what we are going to do today is that we are going to segment some chest X-ray images, some chest radiographs, and basically what we are going to do is that we are going to separate the lung areas from the rest of the radiograph that you're seeing on the screen. Now, a little bit further, you're going to look at those images and understand what this segmentation task is really about. But just notice that this was a public dataset called Darwin dataset. There is a free download link for that. You do not need to click on it or download the data because it's already downloaded and hopefully unzipped here. So in Colab, if you click on this button on the left-hand side menu, this files button, you see the one that my mouse is currently pointing to, you will see the folders and files that is available in your environment. And if you look at here, we have the notebook here, and then we have our data here. So we basically had this darwin.zip file cloned from the GitHub repository, and that final cell we ran basically took care of opening these, extracting this zip file for us. Now, when you look at the Darwin hierarchy here, you see that it has 2 or 3 different folders. The first one we do not care that much about. The second and third one are the most important. So there is a folder for all the images that are basically available in the Darwin dataset, and their manual hand-drawn masks. So whenever we are talking about the segmentation project, you basically have some data. What is that data? You have some images in which you want to segment something. And then you need to have some ground truth data, some labels, against which your model is going to be trained. And where do that data come from? That data usually comes from someone like me or like you, or maybe some experts, radiologists, neurologists, whoever, who have gone through a tedious process of manually annotating and segmenting those areas. And then when those people do that, they usually save the file somewhere, and then they give it to you as data scientists and ask you to train your model, right? So that's the data that we are going to deal with. All right, now we are ready to start the main stuff, right? So we already have extracted the data here. And I'm going to, by the way, I'm going to pause on a couple of checkpoints and ask questions and things like that. But whenever somebody has questions, please feel free to turn on your mic, ask your questions, or type in the chat, and then kindly maybe Farhad or Lindron can let me know that there is a question popping up. But I'm going to proceed for a couple of cells and then pause for asking the question. Now, what we are going to do here is that we are going to first create a list of all the paths to all the images and their corresponding masks that we have, right? Now, I mean, the Python code is probably not that much of a problem for you. It's very basically just using the OS library here and glob library here. But what I really care about is the final here. So you see the output of the cell says that we have about 6,000 images and one sample image name or one sample image path or mask path. You could look at them at their screen. So as you see, they are located in data/Darwin image something.png and something.png for the mask as well. So basically the names for the masks and the names for the images are the same. And this is a convention. Most of the times that you're training a segmentation model, if, for example, your image name is XYZ, you also want your mask name to be XYZ, but located in a separate folder with the title masks, right? So images and masks. You should make sure that those images and masks are actually not confused with each other. Do not save your files with names that do not, make that much sense, because believe me, it happened to me 1 or 2 times that I lost track of which mask was for which image, and then I needed to go through that tedious process of annotating one more time. So just be careful with that. Now, the other thing that we are going to do here is that we are going to take a look at the patient names, right? So one thing that is, in my humble mind, one of the main differences between how we handle the data for medical projects and for non-medical projects, maybe the national photograph projects or whatever things that people usually do in the internet, is that we care a lot about patient names and patient identities. And there are two reasons for that. One, because we basically don't want to reveal any patient identifiers to people who are not allowed to see that data. So patient data is confidential, and that's something very important, right? So if you are dealing with some data and you have collected that data from somewhere not public, like for example, a hospital or your institute, you basically don't want to be careless with that data and let people, maybe some folks on the internet, see the names of the patients. That's most of the times, most of the places, a violation, a very serious violation of the laws. But even more important than that, not more important, but in addition to that, the other thing is that if you do not be careful, if you're not careful with the patient names, then you might have some sort of data leakage happening somewhere during your training that might fool you very badly. So you might end up with a model that looks like to be working very nice. And then when you look at the actual results of that model, maybe when you have solved your model, maybe when your model is really being applied on some totally unseen data, you see that it's basically doing a garbage job. And then you are wondering, you're puzzled, why did that happen? My model looked like to be working very awesome on my training data, right? On my own institutional data. And then why is it showing such a poor performance when I apply it to somewhere else? And that might be related to the problem of data leakage, right? And we're going to talk about that a little bit later. But from this cell, please accept from me that patient names and patient identifiers are important. And this is a serious problem with most of the public data sets that you find on Kaggle, GitHub, or other places. If you look at them, a lot of those usually do not reveal the patient names to you or any patient identifiers to you, which is good. We really don't want to understand the patient names, right? But we do want to understand which images belong to which patient. So maybe instead of saying that the patient names was Pouria, they could say that, hey, this is patient number 10, and patient number 10 had these 5 or 6 images in our repository. Okay, so this is something that is really, really important. If they don't do it, then we are going to have a lot difficulties in understanding and detecting biases in the models that we train on that data. So fortunately, this specific data has that identifier here. So what we're going to do is that we are going to take care of, oh, let's see, maybe I didn't run one cell here, all right. Now, what we are going to do is that we are going to take a look at the patient names here. So we have, now when you look at the Darwin data, let me open it one more time, and hopefully it lets us to open the image folder here. Might take a little bit of time. Let's see if we can load it. You don't do that. I mean, that might probably take your time as well. But anyway, so while that's loading, so the way that the names of the images in the Darwin dataset was organized, here we go. So you see that these images, so you might notice a pattern here. If you look at those files, so that's the reason that I really like this Darwin dataset, because they have the images, and they also let you know that which patient is the owner of the image. So for example, these first 3 images here, they all come from the same person number 88, right? Or this first one as well. But when you go to the next image, they come from, maybe another person. And just look at that. See, some persons have more than 1 images. Some, like this person 89, has only 1 image here in our repository. So it seems that there is kind of a pattern there that we need to figure out how many patients had how many images. And the way to do that is that we need to understand what images belong to what patients. And then for doing so, we need to find out this identifier here, person 88. We need to look for that phrase. And that's what this Python code here that I have put together does. So this is a list comprehension. I'm putting together a list. And how do I find out the names? I go through the path to each individual image. I split the path based on this, path identifier here. And then I pick the last one, which is the name of the file. And then I split it again based on those underscores, because if you remember, the patient identifier was located between 2 underscores. And then you pick that specific name. Now, again, this is not something too much focus of this workshop. So if you don't do that, if you are, for example, used to do that with regex, that's also fine. If not, just go and play a little bit with that. You will find out what this thing is doing and how it returns outputs to you. And then I make it a set so that I make sure I am, getting rid of the main, the repeated names here, and then print the number of patients. So we had about 6,000 something images, 6,106, and we have about 3,636 patients. All right, so this seems like we got more than one images for some of our patients. But there is another thing that we also need to do, and that's printing out some of these names to make sure if we are actually picking up the right data, right? Now, we are basically looking for identifiers like these, identifiers that start with the word person and then have some digits or numbers coming after them. But if you look at these lists, it seems that for some of the images, our code picked up something different, right? For example, this one here doesn't look like a patient identifier to me. This one looks like a full name to me. And if you basically go through these names, it somehow seems that these files might have come from a different data set, right? Because this one, for example, has a COVID-19 pneumonia label in that, which basically means that it's come from a COVID-19 data set. And probably the files from that data set were named differently. They didn't have this person something identifier in their file names. And then we try to extract those person identifiers. For some of these, it doesn't work, right? What does it tell you? It tells you that your data is heterogeneous, first. And second, it's dirty. You probably cannot rely on a code like that to take all the names out of that. And if you want to proceed with these data without cleaning it, we might lose track of some of the important insights that we wanted to grasp out of this data set, like which patients have which images. Now, in such a situation, if you were dealing with a real project, you will probably stay here a lot, and you will probably go through your data, understand, hey, talk with your clinical teams, talk with your mentors, colleagues, whoever who knows this data better than you, and understand why this data is heterogeneous, and how could you find the same patient identifier or person identifier like these for these images. But for now, as far as we want to stay away from any biases, and as far as we already have a lot of data, I just choose the simplest thing to do, and I get rid of those images for which we do not have a person identifier. And again, the code for it is very simple. I'm just going to look through the name of all those images that I was showing to you on the screen, and then make sure that I am excluding those names in which there is not a term like person XYZ, right? So if I don't see that term, I'm going to get rid of that. So for example, here, most of those look like to have that because these are sorted. If we come down, so it's not even showing them here. So you see, we have a lot of valid images, but there is something noisy there as well, because we also saw a lot of unfortunate, images which we did not know their patient identifiers. So I'm going to get rid of those images. And for doing so, I'm going to run the next cell, and this next cell does a couple of things for me. Now, one important thing is that whenever you are dealing with a data set, whenever you have your data curated, whenever you have it clean, at least primarily, the first thing you want to do is that you want to put the data in a format that you are easy to deal with, that you could easily understand, that your Python code could easily go through. So basically, in a format that is more user-friendly. And for doing so, we usually rely on pandas data frame. So again, if you have done a little bit of data science stuff with Python, you probably know pandas and NumPy. So pandas is actually a Python, a kind of a Pythonish, fully Pythonish library that is super handy and very super conventionally used in many other projects. It basically is a library to deal with Excel files, CSV files, things like that. But it doesn't mean that you could put together your data sets in the format of a pandas data frame. Now, what I did here is that I am going to put together all the data that I so far collected, like the path to images, path to their masks, their patient identifiers, whatever, in the format of a pandas data frame, like this that you're seeing on the screen. So the first column, each image has a row for itself here. So every row belongs to a certain image, right? And then for every image, we have obviously its image path so that if I load this path, I could load the image, right? And then I also have the path to its corresponding mask, right? So it's here the path to the mask as well. And at the same time, I also have the patient identifier for that image. So now things get much easier to understand and much easier to analyze, because I have now all my images and mask and patient identifiers in a very much curated and organized format. And how did I do that? Again, that's simple, right? So I'm just going through a for loop. I'm going through all my patient names, image paths, and mask paths, and you basically remember how I actually put them together. And then I'm going to use a zip command here, which basically lets me to go through every single object of these 3 different lists at the same time. And then here is where I get rid of those non-identifiable images, right? I say that, hey, if person was in name.lower, or basically means to just imagine every letter in the name as lowercase, right? Then you are going to append the name of that patient to the patient column, path of that image to the image column, and path of the mask for that image to the mask column. And if it is not, nothing is going to happen. So basically, this for loop is going to ignore those images for which we do not have the person in their lowercase names, right? And then finally, I'm going to put together a data frame here, and obviously printing out the number of records that we had. And we ended up with about 4,000 radiographs. So we lost a lot of them, right? We had about 6,000. We lost almost 1/3 of the data because of the fact that we did not know the patient names for it, right? This is important, guys. This is very important. If you had no other ways, to understand what patients are the owner of your images, you are unfortunately in absolute need of getting rid of that image. And believe it from me, because if you don't do it, I mean, if you have no way to understand where this data came from, if it is only 1 or 2 images, let them be. That's even fine, even if it's mistaken. But if you have 1/3 of your data with no known history where this data comes from, don't use that. This is going to just predispose your pipeline to many biases, and then unfortunately resulting most of the times in the failure of your work. So I don't say that get rid of the data as the first option. No, but that's a last necessary option. If you couldn't identify your data, that's necessary. All right. Any questions so far? Any comments so far? Things that we should... Oh, it seems that there are some questions here. So let me go and look at that. Can we use clustering on the label at first? Yes, Farzan, you definitely could do that. I mean, that's beyond the scope of this workshop to talk about unsupervised type of algorithms. But yeah, I mean, if you have some labels and if you're not sure about them, you could run clustering algorithms, any other. Most of the times, clustering would actually end up separating the data on the institutional level rather than on the patient level, unless some of your patients have a lot of images, right? Which is not something weird for some chronic patients, but most of the time clustering, is not that much of a good tool for doing that. If this happens in reality, you need to go back to your institution, to your mentor, to your colleagues, whoever, and ask them to clean the data for you. Because believe it or not, we are not the magicians, right? We can do something with the data at our own proposal to just clean them up, but we cannot make bad data look good. And as we will see, every deep learning model is as good as the data it is trained on. So if your initial data is not good, then you definitely are not going to have a good model. And everybody is going to blame you for that, which is not fair. So in the first place, just go back to them and ask them to give you the right data. That's very important. All right, now let's continue here with something that is called EDA, or exploratory data analysis. Now, can someone kindly introduce EDA to me if anyone is interested? And just to make sure I am not, behind the time. So Eugene, we have time till 1 p.m. Central Time, right? I mean, 75 minutes.
Yeah, you can go over 1 p.m. If you... Usually people go, sometimes even go until 1:30.
Awesome.
Yeah.
Okay, now we're going to, hopefully we're going to finish on time, but I just wanted to make sure. Yeah, Farzan typed something else. I mean, when our data sets are a combination of some other data sets, clustering that, oh yeah, definitely. Now I got what you say. Yeah, definitely. That does make sense, Farzan. Obviously here, we didn't need to do that because we had those person identifiers that could help us do that. If you have an easy way for doing something and a difficult way for doing the same thing, pick the easy ways. If you just can't do the data separation, looking at the labels, why to go after the clustering, which is trying a deep learning model. You use the data visualization to find patterns in the data. Awesome, Amna, thank you. And then Anna, EDAs to find which features or analysis could be useful in learning from our data. Amazing, yes. You're welcome, Farzan. And then EDA is used to find underlying patterns in the data. You guys nailed that. That's totally true, right? So, guys, there is this unnecessary excitement about deep learning machine learning in general, that whenever you are working on a machine learning project, deep learning project, you should rush to start working on the models, right? Architectures, those fancy things. Let's come up with the next big transformer. Let's come up with the next big ChatGPT, things like that. But believe me, when you come to the real world of practicing deep learning or machine learning, 90% of your time is only spent on knowing your data, curating that, cleaning that, and handling that. And that is much, much, much more important. I quote my mentor, Dr. Brad Erickson at Mayo. In one of my first projects that I did with his team, I had this model that never worked. And it wasn't working in a weird manner because it should have worked. We all expected the model to work. Things were quite good with the architecture of the model. It didn't work. And then Brad told me that, Pouria, whenever your model is not working, go back and check your data. Maybe you're missing up something in your data. And that was really the case with my case there. And let me tell you, that happens almost all the times. If your model is not giving you good results, if your data pipeline, if your model pipeline run into some weird errors, always go and look at your data, analyze that with whatever means that you have in your arsenal. That's something very important. And that's the reason that the name exploratory data analysis came into existence. People really wanted to explore their data. And here, I am going to explore this data with 5 different aspects, with 5 different criteria or 5 different subjects in mind, right? And I will let you know why each of these aspects are important. So that you might consider that a little bit of overkill for the kind of project that we are doing right now, because that's a simple segmentation project that will probably work if we run a model, right? But I will prove to you that that's not the case. And I will prove to you that if you wanted to jump directly to the training segmentation model itself, we would have a lot of difficulties there, right? So let's go through it and understand what is happening. And at step 1, let's start with something that we already talked about, the issue of patients counts and image counts. And I'm probably going to just, when I keep talking, I'm just going to run some of these cells just to make sure that the notebook is not going to turn off. And that if that happened for you, you also please do the same thing. You just run one of your cells that you already ran and make sure that the notebook is active, because sometimes Colab notebooks, turn down their kernels when they are idle after a certain period of time. Now, first things first, let's take a look at the distribution of our number of images per patient, right? So it's a very simple task to do. And, when we work with NumPy, and you know that as a convention, we usually import NumPy as NP in our notebooks. As a convention, we work with NumPy that you need to understand the counts and the distribution of some countable variables. So here, number of images per patient. And how do we do that? We are going to, first of all, take care of, we are going to work with the patient column here, right? And that's basically the list that we added to the data frame. So that patient column is exactly a list of all values in this column. And we are going to use NumPy to take the unique values in that. So this np.unique command, what it does is that it's going to return 2 outputs for you. First, a set of all the values in your list, in our case, unique patients, right? And then the count for each unique patient. So how many times each unique patient identifier was repeated in our list or in our column of patients, right? And then obviously you could use matplotlib, histogram command to just visualize it. And I'll take a look at these and let's ask ourselves what we see here. Let me maybe zoom in a little bit, right? Make things a little bit easier for you. And I can also close this one because I don't think we need that. All right, so looking at this, on the x-axis, you have the number of images per patient, and on the y-axis, you have number of patients. So it seems that you have about 600 something patients which had, who had only one image in our data. And then as we go forward, it seems that we also had some patients who had more than one image, maybe even more than 5 images, or some even more than 10, or even more than 15 images in our data, right? So that's something important. That's something important to know about our data. So basically, the distribution of our data is not like that each image comes from a separate patient, right? This is something to keep in mind. Now, I have put something here. Having this insight about your data will help us to decide how to split the data into training and test sets. Think about that why do we need to do that? Further down the notebook, I'm going to pause and ask you for questions. Not now, maybe after a while. But think about that. Why am I emphasizing this much on understanding which images belong to which patients? And why do I say that this is an important insight for data splitting into training and test sets, right? Think about that. I'm going to ask you about it. Now, step 2. So the first step of EDA is done. We basically understood that our data is not homogeneous with respect to the number of images per patient. Now, in step 2, let's take a look at the original images themselves. Now, this is again one of the big mistakes that rookie data scientists usually make, even some of those very overconfident data scientists, specifically when they are dealing with the data that is not in their own area of expertise. For example, if you are a data scientist with an engineering background and you're dealing with a medical team, and you do know that you do not understand even a single pixel of these images, you don't bother yourself going through those images and taking a look at them. But that's a serious mistake. Both the experts and the data scientists should always, as one of the second things to do in the EDA, should take a look at the imaging data they have themselves, right? So it's very important. We are not going to look at the images after pre-processing them. We are going to take a look at the raw images. And in case of a segmentation project, this has a lot of importance. So here I'm not doing anything, from the code perspective, I'm not going to do anything complicated. I'm just going to put together a figure, subplots from matplotlib, pick up some random rows. So again, if you're familiar with pandas, you know that you basically could sample some rows from that data. And then I put the rows in a random rows list, and I then try to visualize those images and their corresponding masks. And there are, so these 3 columns that you see here, so every row comes from a separate patient, a separate row in our data frame. And these 3 different formats, so the images themselves, the masks separately, not overlaid on the images, and finally, an overlaid version of the mask on the images, are mostly the conventional way to understand and an imaging segmentation data set, right? So whenever you're dealing with a data set, the way that you would like to take a look at your images is like this. You want to have your images, your mask, and then overlay an overlay version of the 2 on top of each other. Now, so we have not so far trained any deep learning model, right? So these are the hand-drawn, these are the manual segmentations, manual annotations. Now we have the images here, so one image, the mask, and then, you also seeing these overlay, which looks like to me as kind of an accurate one. Again, you are seeing the second image, the same one, the third one, looks like the same. The other one, this one doesn't look like an adult to me, maybe a teenage or something. This one, take a look at this one. This is quite interesting. It seems that we also have some non-normal or pathologic lungs in our data set. So this one has a lot of consolidation here, maybe, I don't know, effusion. So that's something that has actually covered half of the lung, right? And look at the mask. Look at the mask. So I need to run this again, maybe just to make sure that they are not idle. Now look at the mask here, guys. You see that the mask, it is a good feature of this data set. The mask is not confined to the boundaries of the air. Whoever expert who annotated this data set knew what they were doing. They did not limit the mask of the lung, because we do not want the model to give up on segmenting the lungs if there is a pathology in there. In fact, most of the times we want the segmentation model to be very solid and robust in segmenting the pathologic lungs even very close to the normal lung here, right? So, and this patient also has some pathologies on their right lung top, upper lobe here as well. So basically, this probably is a COVID case or maybe a pneumonia case, whatever. Now, this cell, shows you some random rows every time that you run it. So what I would like you to do is that, try by yourself, try running this cell a couple of times and see newer images, take a look at that, and try to find out things that might be a little bit weird to you. So for example, here, this is an image that is not probably that much frequent in your data set, but again, it's good to know that. So I'm not sure what this thing is, maybe some wires connected to the patient's skin, something like that. Looks like a device. And it seems that this annotator decided not to include that in the mask. As I told you, every deep learning model is as good as the data it was trained on. So if you train a model on this data set, the model is also going to mimic the annotator here. So be careful with that. That's the reason that I tell you always take a look at your data. And it's not popping up here, but now let me tell you something. When I did when I ran this cell the first time by myself, I saw a very interesting data point which had only one of his lines or her lines segmented. The other one was totally missed, not because of the fact that there wasn't any line, which is impossible, or because the line had something weird with it, which it didn't. It was just missing there. It was missing because probably the annotator forgot to annotate the contralateral line, and this happens, unfortunately. That's reality. People go through a lot of these images and annotate them, and sometimes things happen there. So be careful with your data. But overall, when I look at this data set and I look at some images, they look like to me, quite good. And one important thing, if you are interested in medicine, is that you also should note that the experts who actually annotated this data for us also annotated part of the heart, which is in front of the lungs for us. And this is important because, if you look at, for example, this image, I'm not sure if you are looking at that with the same quality as I am doing here, but look at your own notebook. So you see part of the lung is also visible behind the heart, right? So if you are a radiologist, you never want to miss the part of the lung that is covered by the heart, because sometimes the only consolidation, the only pathology, the only pneumonia signs that you might find in a person's chest X-ray or chest radiograph is basically pathologies that are hidden behind the heart. So those radiologists with sharp eagle eyes, they basically look at behind the heart first and try to see if they find anything there that is mischievously hidden from the other medical personnel. So if this model, for example, was only taking care of the area of the lung which is not covered by the heart, I will not trust that. This is not a good segmentation model. But anyways, this looks good, right? This looks so far good. Now, going back to questions, do we have anything? Yes, I see Farzan has a question. In case like this, maybe our image would not be the same size. In this case, what should we do? Should we crop or resize them? Yes, so the first thing that you need to ask yourself in that case is that whether or not your mask was created by annotating the same image, because sometimes the mask and image are not for the same case, right? Maybe there has been a problem in your data, and this is the 99. This is the answer 99% of the cases. But if it is for the exact same patient and only the mask and images are actually in the different sizes, different resolutions, then you need to resize them. And the only point to keep in mind, and we're going to see that, is that whenever you are going to resize your masks, you need to use a specific interpolation called, nearest neighbor interpolation, which basically does not mess up with the boundaries of your, mask. And this is something that is another problem of this data set that we are going to see soon. Ishika, how does EDA work with unstructured data? So then you need to run a lot of, first of all, every data has some aspects that you could still figure out on your own, even if it is not unstructured. But on that case, I will refer you to what Farzan had already mentioned, unsupervised algorithms. A lot of times you need to go through your data. First of all, run some image processing algorithms. For example, try to understand the distribution of pixel values. There are things like that. But if there are things that you are interested about and your model, you do not have any tool to understand them, then you basically need to even run some models to understand what your data looks like, right? And this happens a lot. A lot of times people train models to only explain their data even before jumping to the main model. So this is important. And thank you for the very nice questions, guys. Keep up asking these very amazing questions. All right, so step 3 in EDA, I know you're tired, I am tired. We are still dealing with the data, but that's how life works in data science. We need to spend majority of our time on data. Let's look at something that basically was just asked in the chat. I'm very happy that you asked that question. It really brings me back to another aspect of this data. Now, whenever we are dealing with segmentation masks like these, what we really want is that these masks, these NumPy arrays, or these tensors, if you speak in the PyTorch language or TensorFlow language, these should be, so in our case, in which we only have one area to segment, this should have only 2 different pixel values. 0 for the background, 1 for the areas that belong to lungs, right? So if you load this mask in NumPy arrays, you do not expect to see too many pixel values because all values are either 1 or 0. If we were training, for example, an instant segmentation model here, that basically, as you now know, segments the left and right lung separately, we needed to have only 3 values: 0 as the background, and then all pixels belonging to this, for example, right-hand side lung should be 1, and then all the pixels belonging to this left lung should be 2 or 3 or 4. Regardless of the exact values, the number of these unique values matter a lot to us. If we are dealing with only segmenting one class on our images, our masks should have 2 unique values. One usually 0 denoting the background, the other usually the 1 denoting your area of interest. Now, even though I myself was putting trust on this data set that this aspect of that was right, it turned out that I was wrong. So what I did was that I went through all those masks that I already saved and, checked the unique values of those masks. So for example, I'm looking at my first mask here. So this is our data frame that we created above. I'm going through the mask column, picking the first row of that, and then feeding everything to scikit-image or skimage, library in order to load that. So a scikit-image or skimage, if you have not worked with that, is something that helps you, is a library that helps you with loading images from these. And that's not the only choice we have. You could also work with Pillow. You could also work with OpenCV, things like that. scikit-image is a very robust, light library that you could use. So I really recommend you to play with that and add it to your arsenal if you have never heard of it. But it's not important here. We have now a masked NumPy array, So, and I'm going to print out the unique values in that. So if it was a true mask, I really expected to see only 2 values here, 0 and 1. But look at what I'm seeing here. 0 and a range of values to 255. What does it tell you? It tells you that whenever these masks were created, somebody somewhere down the line converted them to RGB images. RGB images. Now, RGB stands for 3-channel images that have 200, and in which each pixel in each channel could have 200, could have a value of 0 to 255, right? 0 to 255. So basically, each pixel could have 256 different values. And when you look at these, it seems that, the fact that it stops at 255 tells you that at one point, this mask was converted to RGB, which is a very poor practice for handling the mask. Because for images, that's fine. Change them to RGB, change them to something. You are not going to deal with a very difficult, challenging problem there. But for the masks, nobody should save them like that, right? That's a poor way for saving the NumPy array masks, right? People usually save them as TIFF, or you save them as NumPy arrays or PyTorch tensors, or at least even if you are dealing with PNG files, they still can have ways to save only 0 and 1 pixel values, not this mess here that we are seeing. Now, good thing is that we understood that our masks have such a problem. The second big question is that how can we correct that, right? And for correcting that, things are not very difficult. So if you have, let me run this thing one more time. So if you have had an experience like me dealing with this kind of problems 100 of times, you probably know that these different values all are located in the boundaries. Now, I cannot zoom in here, but if you download one of those images and open it, let me see if I can do that here for you, because that will be a fun experience. So, okay, so let's do that. While waiting for that, what I wanted to tell you is that these weird values, intermediate values, are almost always located on the boundaries of your masks. So the main areas of the mask are always the highest value here, 255, right? Let me open that and see if I can do that. I can download it here, and here we go. Let me open it. All right, so don't be confused that things got to 0 and white, right? Because now we're looking at with a Windows image viewer, and Windows image viewer is basically sees things a little bit differently, visualize them differently. Okay, but now I am zooming in here. So as far as I zoom in on the long, nothing is happening. But now, do you see these shaded gray pixels on the boundaries? These pixels, and I cannot zoom in more than that to show you a better accuracy. So if you have a better software to zoom in on the images like Photoshop or something, I don't want to waste too much time on here, but if you do that, you will see that these values are neither black nor white. These are basically shaded gray, which means these values, these intermediate values you see here, are mostly located on the boundaries. The message for you here is that, so if you get rid of all those values that are not either 255 and 0, you are not going to lose anything important, because only maybe 1 or 2 pixels on the boundaries are going to be missed. And that's a totally acceptable cost, right? So we will jump to cleaning the mask exactly as I told you. I create a folder called, a list called cleaned masks. And then I go through the first 9 rows of my data frame. I load every mask, and then I use numpy.ver command. And what is numpy.ver command? Numpy.ver command is something that helps you to replace the pixel values in a mask with some specific values if a condition is met. So I'm telling the numpy here, hey, go through every single pixel value of the mask. If the value was 255, replace it with pixel value of 1. And if it was anything else, replace it with 0, right? So what happens here is that it goes through this mask. Every single pixel with value 255, which is the areas of the line, are going to be replaced with 1. Everything else, including the background, including all those weird pixels on the boundaries, are going to be replaced with 0 value, right? And then I'm visualizing, so I'm running the exact same command, mp.unique, right? Again, to now take a look at the unique values here. And now compare these values that were returned to us after this mp.unique with these now naturally looking, logical looking unique values that are returned for each of these images, right? So you see, we didn't lose too many things. Now every pixel is sharply either 1 or 0, either 1 or 0. Now you see the value of EDA. If you had jumped through training your segmentation model directly, you needed to deal with a lot of preventable errors in your training and loss and calculations, and you would basically have a lot of difficulties there, only because you didn't spend some time understanding your data. So guys, this is important. This is something that I really want you to bring with yourself home after this workshop. Training the segmentation model, there are tons of notebooks out there that you could go through. If you want to learn only one thing from me today, is that spend time with your data. Look at it, right? This is the most important thing to do. All right, so again, questions, anything here? Nothing, thank you. So let's jump back to step 4, right? So we have 2 more steps in the EDA. Now, another aspect of the data to look at, and this was again one of those nice questions we saw together, was that, the nice questions you asked already, not me, was that what to do with the sizes or resolutions of the images and masks? What to do if those resolutions were different? Do we need to resize them? What is our plan on that time, right? And so this is also another aspect of the EDA that you need to look into. You need to take a look at your images, try to visualize their resolutions, try to visualize the resolutions of your mask and understand if there is any kind of heterogeneity there. Even if there are only 5% of your data that have a different resolutions compared to the rest 95%, you need to take care of that. You need to, that 5% is enough. Even one image is enough to break up your data loader pipeline and, cause an error for your training run. So basically, you always need to make sure all your images and masks are at the same resolution. Now, how do we understand that? This is very simple, but it's gonna take a little bit of time. So I run that first. It's gonna take 1 or 2 minutes to run, maybe on your CPU a little bit even slower if it's not Colab Pro, but no worries, it's going to run fine. Now what I'm going to do here is that I'm going through the entire data frame, right? So this data df.iter_rows give you a chance to loop through your data frame using a for and look at every single row, right? Every single row. And for every single row, I'm reading the image, I'm saving the shape of the image, and you know that these NumPy arrays have usually a shape attribute, which gives you the resolution. So for example, if I have an image with a shape attribute of 512 by 512, it means that, and now you see that Colab is very nicely showing us the values for that, right? So look at here, for example, I'm not going to move my mouse so that you could see that. Now see, we have about 30,984 items, which was the number of images we got, and all the resolutions look like to be 512 by 512 by 3. What this means is that our images are 3-channel, have 3 channels, they are RGBs. So again, they have RGBs. And as you see here, their resolution is 512 by 512. So it means that there are 512 pixels as the width of the image and 512 pixels as the height of the image, right? So everything in the resolution format in Python is usually set in the language of pixels. So we do not say 2 centimeters, we say 512 pixels, right? So what about the mask? So the mask, again, if I wait here, you probably will see that there are also the same resolution, 512 by 512, but they have 1 channel only because, obviously there are grayscale, there are not actual images, so we did not need 5 channels. So, even though I already knew that all these images are 512 by 512, I still put together a code for you so that you can later on use for your own projects. If you had a real project and really want to understand their distribution of resolutions, you needed to plot a chart like this, or maybe 2 charts like that. So here, the chart on the left-hand side is for the images. I probably should have put the ticks for the X and Y axis as well, but please, you probably can understand it very nicely here. So this is for the right-hand side. Oh, sorry, the images is for the right-hand side here, and the mask for this one, right? Now, one thing that you are probably noting here is that the entire data we had for mask and for images have a resolution of 512 by 512, right? So that's the reason that you see only one single point here, because the point for all the data have actually overlaid on top of each other, have fallen on top of each other, only single place here. But if you had a more heterogeneous data set, then you might have seen pixels of different, locations here. Maybe some were 256 by 256. We might have a pixel here. Some could be, maybe even higher resolution than that. So you basically need to run these and make sure that you are looking at the distribution of image sizes. And sometimes people use more fancy kind of plots that also show the number of data points that they see. For example, imagine that instead of a pixel, we could have a circle whose radius could get larger if we had more images on that specific resolution. So there are things that you could do using Matplotlib, Seaborn, and things like that. And definitely feel free to play them out. I don't care how you do it. I just care you do it, right? Do it and take a look at the resolutions of your images and things that might come into your mind and are important. Now, let me also go through the 5th item as well, and then I will again pause for the questions and look at how we are actually dealing with the discussion there. Now, so fortunately, our dataset was homogeneous with respect to the resolution, but there is another thing that we need to look at, and we need to understand for the downstream training that we have ahead of ourselves. And whenever you're thinking about training a deep learning model, you have an inevitable data splitting ahead of you, right? Splitting your data set to training set, validation set, and test set. Sometimes to run a cross-fold validation set. Sometimes, like our notebook, which is a much easier version of that, to just simply, split it to a training set and a test set, right? And this test set is the exact validation set that everybody talks about. So for this notebook here that we are going through, we are only dealing with the training set and a test set. In a real project, you usually have a validation set in the middle as well. But regardless of how many sets you like, you should think about the concept of data splitting. How you are going to split your data set into these different sets. Is that going to be a totally random splitting? I mean, you are going to blindly split your data between these different sets? Unfortunately, this is not the case most of the times. And the reason is that, specifically in medicine, most of the times we are dealing with imbalanced data sets. And by imbalanced data sets, I mean that you have variables in your data that are not as you have variables that do not have a homogeneous distribution of values. Let me give you an example. Say, for example, you are looking for understanding if a patient's chest X-ray has normal appearance versus maybe a pneumonia appearance, maybe versus any kind of lung disease, right? Now, most of the times you have a lot more images for the patients who are normal without any pathologies than those patients who have a certain pathology. And if you're dealing with a data set that has multiple pathologies present in it, like for example, pneumonia, some interstitial disease, maybe some cardiac diseases that are also apparent on radiographs, things might be even more complicated. You might have few patients who have pneumonia, a little bit fewer patients who have interstitial disease, and maybe some patients with cardiomegaly, which is present on the chest radiograph. So basically, you are dealing with these different distributions of pathologies there. And let me tell you, if you happen to randomly distribute your data between your sets and say all your pneumonia patients, for example, fall into your validation, right? So then you will end up training your model only on normal and interstitial and cardiac problems, chest X-rays, whereas your model has never seen any chest X-ray with a pneumonia or with a pathology like consolidation in practice. So whenever it is applied on your test set, now it is facing a class, a label that it has not seen before. And so it is going to mess up because it has never seen that during training, right? So regardless of your task, even if you are training a classifier, even if you are training an object detector, whatever model, we do care about stratifying the split between train, validation, tests, or whatever other sets you have. So our split should be stratified. And now asking you, what criteria may we use for stratifying our data set here, or our problem at the moment, right? Now, obviously, you might say, hey, pathologies. Let's see if we have, for example, a similar share of pneumonia cases in both our training and test sets. And I give all the credits to you, that's right, but unfortunately we don't have the labels for that. Maybe as a couple of our colleagues said, we probably could go and train an unsupervised segmentation model and then come back and have our labels for pathologies and then stratify based on those. Yeah, that's fine, but we didn't want to make things that complicated in this notebook. But I still could think of something very simple that is very important for your model, and you need to stratify that. And that's the concept of the total area of the lung masks. Now, let me go back to one of these images. Now, look at this, for example. You see here that not all lungs have a similar volume here. For example, this person here looks to have a very large lung area, and the mask for that look quite large. When you come to this one, second one, or to the last one, or if you remember to that one I showed you and I said that probably is for a teenage. So the lung areas look like to be smaller. And sometimes if people come from different age distributions, maybe segmenting, because we have structures. We have structures in the radiographs, like thymus, for example, that are visible if you're looking at the chest X-ray for a pediatric patient, for a child. And they're not there if you're looking, for example, at an adult radiograph, right? Or other things that might be different. So this total area of the lung mask is probably giving you a notion about what kind of age distribution, or even sometimes what kind of pathologies the owner of this radiograph had, because there are some pathologies that make your line look larger, some pathologies that make your line look smaller. So even though we do not have the label for age, even though we do not have the label for sex, even though we do not have the label for pathologies, the only thing we have is the mask areas. And that's something that the owner of the data set has not given to you directly. It's your job as a data scientist to pick that up. And how can we do that? Super easily, right? I mean, all of these are NumPy arrays. So we do know that these are 0 pixel values. And then, we have pixel values of 1 on the long areas. So, I mean, if you're a little bit experienced with NumPy, you know that we basically could do something very easy. We could say, hey, NumPy, please sum all pixels in a single mask to me. What it is going to do is that it's going to sum the pixel values for all the pixels in a single mask. Remember that all pixel values anywhere except in the lungs themselves were 0. So those are zeroed out. But all the values that you have for the pixels on the lungs, they are going to sum up to some values. And if that value is large, this basically means that you had a lot of lung area there. And if it is a small, it means that you had smaller lung area. Now, again, I'm just creating a list of these sums here and then adding that back to our data frame as a new column, right? Now we have a mask area. Now, if you ask me, what is the unit here? The unit is pixel. The unit is pixel. So this basically means that we have 86,000 pixels in the radiograph of person 0, which belong to lungs. And if you compare it to the second patient probably had a larger lung, right? So that's how we do that. Now, let's visualize the distribution of these mask areas. Again, we use the familiar Matplotlib histogram functions here with 100 beans. And look at that. At least their distribution was normal, right? This is a normal distribution. This is how you and I expect the long volumes to look at, right? This basically gives you some insight. So if you are, it's your job as a data scientist to always consult with your medical experts, with your domain experts. So if you show this plot to someone who is a physician or maybe who is a pulmonologist and looks at this and say, hey, I guess, yeah, probably your population was normal. It's good news. Your data set did not contain the majority of the radiographs coming from, for example, patients with pneumonia or patients with, for example, I don't know, asthma or patients who have larger lungs or smaller lungs. No, it seems that, both the annotation of the lungs and also at the same time, the background pathology look like to be normally distributed. And that's good news. That's good news. Yet, we still need to figure out a way. For splitting our data in a way that the data splits are stratified based on this mask area. And I would like to also ask you back regarding that question I mentioned I'm going to ask you earlier. Why did we need the patient identifiers if we are going to do the split? How the patient identifier comes to play here? And I'm going to ask that, but before that, I see Farzan asking something again, and also Amna. So let me make sure I'm not missing anything. All right, so Amna first. In the ADA, we saw that there was a distribution of, let's see, there was a distribution of number of images per patient. So maybe we need to test distribution to match our, let me understand your question better. Number of images per patient. So maybe we need to test distribution to match our training distribution. So, not quite the answer I'm looking for, but that was a nice way of thinking about that. So thank you, but no, that's not the answer. Now, Farzan, in that case, I think at first we should split the whole data and then shuffle them and pick up randomly. That's also a good way to do that, but we have an easier tool for doing this, and I will introduce to you shortly. Having the same patient's X-ray in both training and test would cause bias. Awesome. Anna, that was totally right. That was totally right. Whenever we are splitting our data between training sets and test sets, or whatever other sets, we should care about two concepts. One, grouping, second, stratification. And one is much more important than the latter, right? The former is much more important. Now, what I mean by grouping is that you don't want to see images of the same patient in different sets. If patient 10 has 20 images in our data set, and the first 2 images of patient 10 has gone through our training set, say for example, we do want we do want other images of the same patient to also go there. I'm not sure what I did that I messed up this one. Hopefully not something very important, but let's see. Name mask areas is not defined, so maybe I needed to run that one. Okay, all right, see what happens. All right, so yeah, that's fine now. So this is important. You really want all images for the same patient to go to one of the sets, because if the images go to different sets and your model gets good at segmenting that image that is in the validation set, it doesn't mean that your model has really learned anything. You know, the distribution of the long shape in two different radiographs is not that much different. So your model might be overfitting to your training data, and it still does a good job on segmenting the image on your segmentation, on your validation set. Why? Because the image in the validation set and the image in the training set came from the same person. We don't want that to happen, right? Let me tell you, if you have multiple CT scans from the same patient, if you're working on 2D medical imaging from CT and you have multiple slices, multiple axial slices from the same patient's CT scan, whatever that you have, always, this is something very important, red line, always distribute your data based on the patient IDs or whatever patient identifiers to have. Whatever data that belongs to a single patient goes to the same set. Even if you think that your model will not learn anything if that leakage happens. Let me tell you, the leakage happens and the model is going to cheat. Don't fool yourself. Always put all data from the same patient in the same set. That's very important. And we also talked about the stratification, which is the latter thing we need to do. Now, how do we do things like that in reality? Do we really go there? And because if you're a programmer, you know that hard coding things like that is gonna take a lot of time, or you need to run a lot of sanity checks to make sure everything is working fine. But fortunately, we have a very good tool at our arsenal that is going to help us a lot here. And that tool is one package from, or better to say, one class from the scikit-learn package. So this class that you see here is stratified group k-fold. If I scroll all the way up, you see here that it is imported from scikit-learn.model selection. So we have a class called stratified group k-fold, and it is a very nice class. It helps a lot. How does it work? It receives from you your data, the variable that you want to use for grouping, and the variable that you want to use for stratifying. And you can also have multiple variables for stratifying. It also receives a random seed from you. It asks you if it needs to shuffle the data for you or not. And then very simply, it just goes through your entire data. And this is the way that you need to put this command into use. You might ask yourself, hey, how does it work? And it looks a little bit complicated. It's originally designed for cross-validation type of a split. So basically, if I want to have 80% of my data to be present in training and 20% for the test, which is the case here, so at 80-20 split, what I do is that I evenly break my data to 5 different data sets of roughly equal size, and then pick the first 4 ones as the training set and the last one as a test set. So that's going to be an 80-20 split. But most of the times, this class is used by people for cross-validation, and that's the reason that you don't see something like train test split directly here. It helps you to break your data into equal sized folds. And that's the way it works, right? And then there is another nuance to this class that you should be aware of, and that is this class, that scikit-learn class, doesn't work with an stratification variable that is quantitative. It is going to mess that up. It expects you to give it a qualitative, a categorical kind of, a stratification variable. So that's the reason that I here, just beanify my mask area and put them in 10 different beans. It is very simple, right? So this pd.cut is a command in pandas that helps you to bean a column into a new column. So I beamed the mask area column into 10 different beans. So just imagine that we are plotting a histogram of all these mask areas in 10 different beans. And I put it like that, and then we have it here. And then this is now a categorical variable, right? Because this is a string. So this kind of tuple that you see here is actually stored as a string in this column. So the scikit-learn looks at that as kind of a name. Say, so this is bean 1, this is bean 2, this is bean 3. I always do not give arbitrary names to these beans because I really want to understand what range of values each bean actually covers. So that's the reason. But the scikit-learn is going to take a look at that as kind of a string data. And then when I'm going to run the scikit-learn stratified group table command, I'm going to give it my main data frame, the variable that is going to be used for grouping, for stratification, which is mask area bean, and then the variable that is going to be used for grouping. So, and what it is going to do, it is going to give me a new column here called fold, right? So it's going to distribute the data into 5 different folds in a way that all images for the same patient goes to one fold, and also in a way that each fold contains a similar distribution of mask area bean variable, right? So basically it stratifies and groups. And now, as far as I'm not running a cross-fold validation here, and I'm only caring about a training and test split, I simply, set the set column here as test whenever the fold is 5, and in 4 other cases when it is 1, 2, 3, 4, I set it to train, right? And then show the data frame again. So you see why these pandas data frames are so user-friendly and handy, because when we first started putting together a simple data frame with 4 columns, 3 columns, and then added 3 or 4 columns of our own on top of that, that's how easily you could actually play with data using pandas and using whatever these data science tools you see here. All right, now before we go to data transformations, one more thing to check. So whenever you run your data split, even though this function, this class is actually pretty much tested out, it works very nice, you should always check your data by yourself. You should be very obsessive, guys. I mean, just always try to check. So I am trying to double check if any patient is in both the train and test sets. And this is a simple assertion command here. It doesn't matter what it does. I mean, you could just go and check it. Again, it's using pandas and the intersection command of that, which basically checks if something is in both 2 of the different subsets of your data frame. And then finally, I would also like to take a look at the distribution for my mask areas in the training and test set. And for that, I visualize something which is called a KDE plot. So KDE plot on the x-axis shows the mask areas, and on the y-axis it shows you something called density. So it's not percent, it's not it's not percentage, it's not frequency, it's density, but it's highly correlated with the frequency here. So what you see, and I use Seaborn. So this SNS is actually the convention to import Seaborn package. Seaborn is a package like Matplotlib. It basically gives you more fancier plots like this one that you see on the screen. And this is the normal plot, that normal population plot we were looking at before. And now I have actually overlaid the same plot for the training and test sets on top of each other. And you see that basically those are pretty much the same. So we have not messed up our stratification. This all, we have gone through 1 hour and 15 minutes of talking, and we are now up to the point that we should start putting together our transformations, augmentations for training. So everything we did so far is data handling and data cleaning, and still we're going to deal with data, at least for the sake of transformation. But guys, believe me, in a real project, you're going to spend 100 times more than that on data cleaning. Data cleaning is important. Keep that in mind. Now, going back to questions here. Let's see, what do we have? All right, so starting from here at the OpenCV libraries, I think it would be GBR instead of RGB. I am never good at OpenCV, but I guess you're right. So I usually use that only from case by case, not very regularly. So Andrew, I believe, was answering one of the previous questions. Thank you, Andrew. Dean, Amna. In the EDA, we saw that there was a distribution. All right. Oh, so maybe I just missed that one out. That basically was a repetitive question. So let's see. That one. All right. So no new questions, no new comments. Guys, do you have anything to ask or any opinions to share? Anything that you would like me to pause on before proceeding to the next section? I know the EDA section was long, but that was necessary. Anything else, or shall I proceed? Eugene, do you have any points or comments, things to make? Are we good? People are asleep. Everybody's listening.
Yeah, it's good. We can keep going, I think.
Sure. All right. I'm still thinking that we probably can finish on time. So let's jump back in and see what we will see. All right, now data transformations, and here is the regular stuff. So what do we mean by data transformation? Data transformation is actually a pipeline for pre-processing your data, right? So what kind of pre-processing? Say whatever things that you need to do. I guess I need to run something else again here. Oh, I didn't run any of these. Let's do that. Okay. So what actually means is that we are going to put together a pipeline to read our data from these, take care of all those things that we found are necessary during EDA, like, for example, correcting for those mask values that were messed up, resizing our images if needed, and then obviously augmenting our data in the training sets, because we are going to train a model, and the model basically needs to be trained on something that is a little bit more robust compared to real data. So all of these are called data transformations. And here is where, in my humble opinion, the package Monai shines a lot, because Monai has a lot of use cases. We're also going to use Monai networks and loss functions and metrics. But honestly, if they ask me that, hey, what is the first thing, what is the most important thing in Monai that you want us to keep and maybe lose all other things, I would say the data transformations. That is very important. And you could click on this link and go to Monai Transforms page. That is going to be super handy. It has a good documentation there for you. Monai also has a lot of good tutorials on their website if you really want to go through a couple of other notebooks to feel more confident playing with that. So feel free to play with Monai. As far as you're in medicine, you're dealing with medical imaging data, and you want to, don't get into very nitty-gritty technical details and those tedious work of data processing and things like that, Monai is a very good help to you. And believe me, I'm not a fan of these high-level packages like PyTorch Lightning and things like that. But honestly, I found Monai to be super awesome. So a lot of kudos to their team. And let's give credit to them before proceeding. All right. Now, how do we actually work with Monai and put together transformation pipelines? It's not super difficult, right? Monai has this nice functionality that lets you apply separate transforms on different objects. What do I mean? So we are going to train a segmentation model, which basically means that in every batch during training, our model needs to see images and their corresponding masks, right? So the data processing pipeline, unlike, for example, a pipeline in a classification project, which need to only handle one image for you and then handle a label, in this case, it needs to handle two different images, one the main image and the other the mask. And maybe we need to apply different transformations on top of each of these, right? Maybe we need to do something with our images that we do not need to do with our masks. And if that's the case, then we definitely need to have a way to apply different transformations on each of these. And Monai gives us this nice feature that we could actually apply our transforms on different objects. And for that, they have a variety of their transforms that they call dictionary transforms, right? And by dictionary transforms, it means that, hey, for example, I have this load image transform here, and you see this D at the end of this name. And you also see this D here, and you see also this D here. And these Ds could be capital or lower letter, no difference, both of them work. And what it means is that, hey, I can give you the capability to run me differently when I'm applied to your image versus when I'm applied to your mask. And that's a huge win. And that's why Monai really, really shines. If you wanted to hard code that using pure PyTorch, then you needed to put everything together on your own and make sure that you are applying augmentations, transformations to the exact object you're looking for. But with Monai, things are simple. The only thing that this kind of pipeline, such a pipeline needs from you is that you need to have your data as a list of dictionaries. What do I mean? Let's first take a look at this output, right? I want to have for each image a dictionary like that, and then stack all these dictionaries for all my images in a list. Now, what is this dictionary? Very simple. It has, the most important things that Monai is going to use are these two lines: a separate key for the image, a separate key for the mask. I also always include the metadata I have for that image, like the patient, because down the road it's going to be useful. And also some other variables, like, for example, which set it belonged to, what fold it had, what mask area bin it had, what mask area it has, things like that. And you might ask me, so we had everything like that in a data frame. How do we get this list of dictionaries? So basically, I want to change every row to a dictionary, right? So it turns out that pandas, again, the very powerful library we love, has a very simple way for doing that. It has something called toDict, and it receives an argument called records, right, from you. So I say, hey, my train data list. So basically, I want to have two separate lists of dictionaries, one for my training data, one for my test data. The reason is these two different data are going to see different augmentations during training. One is not going to be augmented, the validation or tested one. The other training should have some transformations for augmentation. So that's the reason that I didn't put together a single list of dictionaries for the entire data. We need two different lists, one for training, one for test. All right, how do we do that? This first part is very easy. We just say, hey, this is just subsetting a set of our data frame, right? I'm saying that, hey, go to my data frame, and I'm only looking for part of the data frame for which the column set has the value train. This is this part, right? And now when you get that data frame, I'm going to pipe another command with that. Hey, make it a list of dictionaries, and this keyword is important. You should pass the keywords records here, which means that now the dictionary is going to look like that, right? And then I do something similar for the test set, and then I print out the number of train and test state records. And so we have about exactly what we're looking for: 3,000 data in our training, 800 something in our test set. And then obviously I also visualize the first dictionary in the train data list, which was that object we were looking for, right? So that's super simple. And then when you have this, then you can feed it. Then you can feed it through your Monai transformations. And let me first, before going through the transformations, let me first, come to this cell and show you how you are actually going to apply your Monai transforms and build a PyTorch data set, right? So look at these two lines, for example. Obviously, in PyTorch, we need to have a data set, and then we are going to feed that data set to a data loader. This line you already know about. Definitely, you need to have a batch size and shuffle. But the question is, where did these data sets come from? And the data set came from a specific type of data set that Monai has, and it's called persistent data set. Now, Monai gives you a lot of different dataset formats, right? And the dataset formats are independent of your transformation. So if you're dealing with, for example, it's not like that if you're dealing with, dictionary transformations that you necessarily need to use persistent dataset. No, that's not the case. I mean, you could use whatever transformations with whatever type of datasets. I personally always use persistent dataset because persistent dataset runs much faster than others. The way that it works is very interesting. During the first pass on your data, during the first epoch, in other words, right? It goes through your data and it goes through all these transformations that you put together. And for example, for the training data, it comes through the first point, then where a random transformation is going to start here, right? Because if it is random, then it means that now this should happen differently for every batch and during every epoch. Right? But what about these 4 transforms, right? We're going to talk about that shortly, but those are the transforms that are going to be repeated every time that you see that data, right? They are not going to change. So what the persistent data set does for you is that it says, all right, during my first pass, I'm going to inevitably be slow and go through your entire pipeline. But from epoch number 2 onwards, what I'm going to do is that so during the first epoch, I'm going to cache the entire data you had after these non-random transforms, on a folder that you specify for me. Look at here. I have specified a cache directory, which is going to be created soon when we run these cells. And I'm going to save those cache data points there. And from epoch 2 onwards, I do not need to run everything from scratch. I'm going to just load those pre-processed objects from the disk and just feed them through the random transformations. And the result is going to be that your epoch 2 to your final epoch is going to be much, much, much faster. So your epoch 1 might take 15 minutes in a real project. Your epoch 2 is going to take 1 minute. So that's the magic of persistent dataset. Monai also has a couple of other datasets that do something similar, but with a little bit different technological behind the scenes. But basically, this persistent dataset is a good choice if you just want to proceed with that. So far, we have not done anything fancy. I first make sure that if there is any cache data set, I get rid of that. And then because you need, so every time that you change your data, you need to remove your cache as well. This is important. But then you see that here I'm putting together 2 different data sets and 2 different data loaders from my training and test set. And each of these data sets receive their own transforms, which we defined above and we'll review now, right? Train transforms and test transforms, right? So this is fine, hopefully fine, and hopefully clarified to you. Now let's come back here and take a look at this. Let's see if this one works. And all right, okay. Now let's come here. I'm going to hide this one and then get rid of this one. Hopefully the notebook doesn't crash before we run our training. But anyway, so let's take a look at these transformations. Now we have 2 separate pipeline of transforms, one for test, one for train. A lot of things are in common between them. What are in common? For example, loading the image. We are going to load the image with this first line. The keys are image and mask because both need to be loaded and we are not going to change them. Second, now look at here. We are going to only apply something on our mask. And this is called a lambda transformation, which helps you to apply a quick function on your data during the pre-processing pipeline. Now, what am I applying on my mask here? The exact same thing we discovered before. I am telling the model, I'm telling the Mona, hey, during your pre-processing, get rid of all the values except for 0 and 1 and replace them as we did before. And this is equal between the test and train transforms because we want our masks to be sharply accurate for both of these pipelines. Now, this ensure channel first dimension, what it does is that it makes sure that your images are channeled first. If three channels images in TensorFlow are usually channeled last, which basically means that the first dimension and the second dimensions are the resolution, say 512 by 512 by 3. And this was also the case with our images as well, right? Because if you remember, that 3 was in the end of the tuple. Now in PyTorch and Monai, the way that PyTorch deals with data, they usually want the images to be channeled first. So instead of 512 by 512 by 3, they want the images to be 3 by 512 by 512, and for the mask to be 1 by 512 by 512. So that's how things are done using the ensure channel first D. And then I need to transpose the images, basically rotate them for 90 degrees because it's a weird stuff with the load image transform and Monai. It's use ITK behind the scenes and that transposes the images. So this brings the images back to normal looking. And then up to this point, everything was pretty much constant, right? But now let's take a look at, and everything was also present in the test transforms. But now let's take a look at only those transforms that are available in our training pipeline. So a random rotation, and you see here, I'm using a random rotation of minus 0.5 to 0.5 gradient. And this is just to make sure that you know that this is in gradients, not in degrees. This is very important. And then I'm asking the Monai to apply this with a 50% chance of happening. And I could also change these chances or maybe even the ranges for images and masks if I feed in, for example, 2 different lists of tuples here. But what I'm definitely changing here is actually the mode of rotation. So guys, one important point here is that whenever you are dealing with your masks, you should always deal with nearest neighbor interpolation, never with bilinear or bicubic or any kind of those interpolations. The reason is that if you use those kind of interpolations, the 0 and 1 values that we had are going to again change to something between 0 to 0.2, 0.3, 0.4. So you're going to mess up with your mask values. Take home message, always play with your mask values using the nearest neighbor interpolation. So this is a random rotation, then a random flipping, make your images, right to left, left to right, and then finally resizing. And for the sake of resizing of this image, I'm just sticking to a 128 by 128 resolution. Obviously, this is not a very high resolution. So if you have access to a better GPU other than Colab, I believe even this one might not work on a regular Colab without the Pro version. But you could basically make this 32 by 32, 64 by 64, whatever you like, right? So this is your pipeline. And then after that, we scale everything. We scale the images between 0 and 1. Please note that we are not scaling the masks because masks are already either 0 or 1. But for the images, we usually scale everything between small values like 0 to 1, -1 to 1, The reason is that we don't want our gradients and values to explode during the training. So even though our images had values between 0 and 255, as they were RGB images, during the training, we usually scale them between 0 and 1 or -1 to 1, however you like it, right? And then finally change everything to PyTorch tensors. And if you look at the test transforms, they have everything except for these 3 lines that are for augmenting the data, which we do not need during the test transforms. And the other cell we already know, so let me run this cell and then jump back. And then we have this train DS and train DL. And now let's do something funny. Let's get a batch out of our train data loader and visualize that. And the batch size is 8, so we're going to have 8 different images come back. So I run that cell, and what happens is that after a few seconds, this matplotlib subplot is going to be shown with each image in one row along with its mask. And now look at these rotations. These rotations are coming out of our own pipeline here. Right now we are rotating. This image is flipped because, as you see, this is the left side of the patient now coming to the left side of the screen as well. The reason is that now it's flipped left to right, right to left, right? Now you might ask yourself, do we really need this kind of flip augmentation? That's a good question if you're asking that, because not too many people have their heart on their right side. Some people have dextrocardia, but those are not very common. So yeah, I mean, you could say that we probably could get rid of that. I put it here because for most of the segmentation tasks you're doing, flip is a good one. But in this specific problem, in this specific project, we could omit that and nothing could change, right? So I don't think even if we have one case of dextrocardia in this data set, but anyway. And dextrocardia is referred to those patients who have their heart on the right-hand side, and many other, many other organs in their body also flipped out. And that's something that is very rare, but it's there. So basically. Anyways, now look at the size of the images as well. They are 128 by 128. If we go top, I'm not sure if, for example, here, you see, these were 512 by 512, right? But now coming out of our pipeline, they are 128 by 128. So they have also successfully resized the images. Now, this really brings us to the end of the discussion for data. And then we have 2 shorter discussions to follow on model loss and metrics, and then finally the training. Now, very quickly, anybody asking for questions here? Nothing on the chat. Anybody wants to turn on the mic, jumping down and up, asking for questions? Anyone? People said that whenever you're teaching something and there was a huge silence like that, there are 2 possible scenarios. 1, everybody is understanding everything. 2, nobody is understanding anything. Hopefully that's the former case with you guys, but no. I am at least doing my best here to make sure that things are clarified to you, but please feel free to interrupt me, feel free to ask questions. Eugene was very kind to me to say that we have times even more than that. So please feel free to jump and tell me if you had any questions. Thank you, Farzan, for the heartwarming message there. That's cool. There was something else. Okay, so let's see. I'll feel good. Thank you, Annie. Now, guys, let's go back to the model loss and metric. Right now, there are different ways that you could segment, that you could have a deep learning model to segment your images. But the one that is very famous and the one that has inspired a lot of other architectures is called UNet. It goes back to 2015, where the original paper came out, and that UNet model is called Vanilla UNet. Even right now, after 8 years, it has a very good performance. A lot of people tend to use that one instead of playing with the other variants of UNet. But there has also been a lot of different architectures that have followed this UNet-like kind of architecture. And even without me explaining the architecture, you can probably guess where the name comes from. It comes from this U-like architecture that you see here. And a lot of different architectures follow this similar convention without necessarily following the exact architectural choices of the original authors. But all these models are most of the times referred to as UNet. So the next time that you heard the name UNet, you should ask yourself, or maybe the authors, or maybe the data scientists, that which UNet they are referring to. Are they referring to the vanilla UNet, which was originally proposed in 2015, or are they referring to a UNet-like architecture that has now many more fancier, many more complicated features in its architecture. So that's something to have in mind. But we keep referring to this unit here that we are going to work with as a flexible unit, and then we'll tell you why. Now, so the original unit that came out and has this image here, it was very simple. So it consists of a couple of convolutional layers that start with an input image of size, say 512 by 512, or maybe 572 by 572. And then, bring the image back to lower resolutions, to a bottleneck. This part of that is called the bottleneck. And the idea here is that to force the model to pick those really, really important insights from your original image, and then gradually bring it back to your final resolution, to the resolution that you were looking for. And it doesn't necessarily need to be the exact resolution of your input image, but most of the times it should be, as I mentioned before. So again, I'm going to run this notebook, run this still one more time to make sure we are not idle. All right, so this is the area, the idea of UNet, to start from an input image resolution, go back with convolutions, and then go up again using reverse convolutions or upsampling or up convolutions, however you like to call them, and then coming back to the resolution of the image. So the image is fed through your model, change, and the mask is coming up. So the original image might have 3 channels like the ones that we have here, but the output image is going to have only 1 channel, right? And also note these gray arrows here. These basically are the skip connections. So the kind of connections that you also see in ResNets, and they were basically introduced with ResNets, and the name residual block came after them. So basically, these are the same things here, make the models more robust. But the idea of UNet is not very complicated. Feel free to read their papers. Again, there are tons of Medium posts, papers, GitHub blogs, whatever you like, that have explained them. And I'm not going to jump into the details of the architectures here. But one thing that I would like to introduce to you, because I want to keep things practical here, is that so the original vanilla UNet is also present at Monai if you want to take a look at it. So if you go to Monai, let me do that for once, at least in this workshop, because I believe it's worth of your time. So this is the Monai webpage. If you come to docs, say Monai core docs, I believe, hopefully I'm in the right place. And then you come here, there have a lot of different things here. So for example, project Monai, so let's see if I can find the features here. So usually what I usually do here, so they have a lot of models here. So what I usually do, for example, if I search for transforms, they bring me to this transforms page. So you come here, you see here, now this is the actual doc. So they have a lot of different things. So the dictionary transforms that I talked about are here. You could go there. For example, this is the, let's say, one of these that we picked and used. For example, this load image D was the first transformation we used. And then Monai also has a lot of other things, right? So transforms are, in my opinion, are the most important ones, but they also have network architectures. So if you come to network architectures, you see they have blocks, layers, nets, and utilities. So even if you are interested in building your own model, just using some blocks from Monai, feel free to check out here. But if you go to nets, then you have all these networks here, and those are pretty much biased towards medical imaging. So all the models that you see are famous in medical imaging for are already out there. And a lot of time you find things here that you do not find elsewhere, like for example, in the PyTorch models. So one of the things that you really find here, I mean, you easily find here, so for example, the vision transformers, VNet, UNet R, which is a UNet and transformer, the vanilla UNet that I wanted to show to you. And you see it here. I mean, this is basically the original UNet that was proposed in that paper back in 2015. But the one that we are going to use is called flexible UNet. Now, flexible UNet, as you see, receives a lot of input arguments. Why is it called flexible? Because it helps you to change the backbone or the encoder of the UNet with something that you like. Now, what is the encoder? I forgot to introduce to you earlier. So this first part in which we go from a high resolution to a low resolution is called an encoder, because it's somehow encoding the image into the bottleneck, into a very linear vector. And the second part is called a decoder, because now it's receiving the encoded vector and bring it back again to the image space. So encoder, decoder, a UNet in the first arm is an encoder, the second arm is a decoder. Now go back to Monai, and then you see that they say that they can now replace the encoder with a lot of fancier architecture. So basically improve your UNet from what it was originally. And you could use different things here. You could use, for example, whatever classifier networks that you know, you could theoretically use instead of an encoder for a UNet. For example, ResNets, efficient nets, things like that. So the ones that I really recommend you to try are using efficient nets for the encoder of the UNets, right? And this comes from a guy called Lucamlas, I believe, who originally had his own GitHub, but after a certain checkpoint, his models were merged into Monai. So again, this is a very good and tested out kind of class to work with, flexible UNets. Now let's go back to our own code here and proceed. So here we are going to define a model. Now, the model we define is going to be a UNet. So it's going to be pulled out from mn.networks.nets.flexible UNet. And again, the convention is to, usually, as you might have also noticed in the transforms I forgot to mention earlier, the convention is to have Monai be imported as mn, like NumPy as np, Monai as mn, pandas as pd, things like that. Now, what kind of arguments it receives? The input channels, so the number of channels that your input images have, which for us was 3 because our images were 512 by 512 by 3. What is the number of your output channels? So here you could have only one channel because we had only one class, but I wanted to keep things practical for you and said we probably want to have, if you're, for example, dealing with a segmentation problem that has more than one classes in it, say, for example, you are segmenting the heart and the lung at the same time, you really want one output channel per class that you are segmenting. So in this case, we are literally segmenting two classes, right? The background class and the lung class. So we needed 2 channels. Now we could make it one channel output, and in that case, it could be 1 pixel. And if the pixel value, for example, in the prediction was above 0.5, you could say, hey, the model thinks it belongs to the lungs. And if it was less than 0.5, you could say the model thinks it belongs to the background. But the more usual way for doing that is to have your model output a multi-channel output in which every channel belongs to a certain class, and your background class also has a channel. And usually the background has the first channel, channel 0, right? So that's the reason that you see here we have 2 channels as outputs, one for the background, the other for the lung area. Obviously, the magic of this flexible UNet is the backbone. I picked efficient net B0, which is the smallest efficient nets, and the one that is least likely to overfit to our model, and the pre-trained argument, which is set to true. Now, one brave guy or lady, please speak up and say, what does this pre-trained argument do for us here? What do we need that? What will happen if you do not put it there, if we set it to false? Coming back to questions. Anybody wants to answer? It means we are using a model that has already learned. Absolutely right. Thank you, Andrew. Now, where did that model learn from? Where it was trained on? Let me go. Someone else trained it. That could be theoretically right, but this is not the case with Monai, right? So a lot of time, not a lot of time, but sometimes if you have very good data sets, in your institute, you, for example, train a model on your own and then learn from that. I mean, you start the weights rather than start them quite randomly, start the parameters of the model quite randomly without any knowledge of your problem. Sometimes you start it from a checkpoint, from some weight values or parameter values that you already knew because you already trained another model. So that concept is called transfer learning, because you have a first model, it has learned something, and then you transfer the knowledge from that. You transfer the weight values from that to another thing, to another model that is now going to learn something new. And if this model is going to learn something new from scratch, it's going to have a bit more difficult job compared to the time that it starts from some knowledge from another person. So these two jobs are not necessarily the same, right? So you could have basically trained on a separate task and then transfer learn to train another model for a different task. But as far as the data for these two are the same and the tasks are not that much different, you basically are going to see some improvement in your results using transfer learning. And now I see some responses here. So using a model which has been trained using a larger data set, nice answer, but not true for Monai. Depends. For example, I think EfficientNet was trained on 14 million images, and I think it would need fine-tuning for medical image. You're right, Farzan. So this, I mean, whenever you deal with transfer learning with Monai, PyTorch, things like that, usually they are transfer learning from a very huge and famous data set called ImageNet. So ImageNet is a very huge data set of millions of natural photographs that, is kind of a standard baseline data set for training deep learning models. People usually first train their models on ImageNet and then transfer learn from that. As far as this data set is huge, we still see some improvements in our medical model if we transfer learn from ImageNet, which is very weird, right? Because ImageNet is a data set full of images of cars and horses and things like that. And then you ask yourself, how is that going to help a model understand the long areas? Well, if you knew deep learning in a good level, you would basically know that these convolutional layers usually pick up very, very fancy small details or features in the first layers, something like edges, corners, things like that. And, the chest X-ray is not that much different compared to a dog image with respect to the corners and, curves, things like that. Yeah, I mean, the high-level features are different. We are never going to see the ear of a dog into a chest X-ray, but we are going to see the same sort of corners, edges, lines, boundaries, things like that. So we still, I mean, if you had a very large medical data set and your model was trained on, definitely it's better to transfer and learn from your medical model. But if it is not, and most of the times we do not have such models, we transfer learn from ImageNet, and it's still better. And the term for retraining or better training a transferred model is called fine-tuning, as far as I mentioned, with a little bit of simplification, because in fine-tuning you usually do not train your entire model, only the top layers. But in retraining, we usually go through training the entire architecture. So that's mostly retraining here. So if I go back to the notebook, what is happening here is that, as you can see, first of all, this is the guy that I mentioned to you, Lucumelas. So this the Monai behind the scenes is picking up the weights from his GitHub repository where the efficient flexible unit was originally developed, and then loads that out and also loads the weights from that GitHub repository. The models which were trained on ImageNet are going to be transferred to your model, and now your model is going to learn on top of that. Now, we already do that. Let's do it one more time. And then I commented out this cell, so don't do that in your own notebook if you like. I mean, this is going to make things a little bit dirtier, but if you want to print this model out, you will see a lot of things here, right? So just look at here from the top. Flexible unit, efficient net, B0 encoders. Look at all these different convolutional blocks. So these are, so you see, if you wanted to develop the model by yourself, you needed to go through something like that. You need to put together convolutional blocks like that and do many things like this. And then finally, you come up with a model that is going to do the job for you. But thanks to Monai, we don't need to do that, right? The model is already loaded for us. Now, let's load an image. And guys, I just noticed that I'm past time. I probably need 20 more minutes. So again, thank you for your kind hospitality, giving me more time to proceed. But if any of you needed to leave, I already apologize for the delay here. I tried to wrap that up before.
No worries. I personally am really enjoying the step-by-step explanation. I think this is our last workshop anyway, so I think it's a good point for everyone to understand UNet more or less completely anyway. So please go ahead.
Yeah. Thank you very much. That's very kind of you. Very kind of you. Thank you all. And sure, no, I have time today, so I'm happy to proceed. And then at the end of the time, as far as you have questions, I'm happy to answer them as well. But again, so if anybody wanted to leave earlier, I'm sorry for that. Anyway, so we have the model, and we already have a nice model that is not trained on our data, but has some sort of pre-trained weights. And let's put it into use, even without training. And we already had a batch, we had our data loader ready, so we have everything. And it's a very good practice for you guys. If you have a model ready, before even starting to train that out, just feed one batch of data to your model and see if everything is working fine. So if your images could go in and then come out, solid, then that's good news. That means that at least your model is working and everything is fine with that. Because training itself is complicated, so we really don't want to go there without knowing what we are doing. If a bug happens in your training, you want to make sure that the bug is not with your data nor with your model, and you need to figure out the training pipeline itself. So always check out things step by step. Now here, we have, let's say we had our dummy batch. If you remember, we got it. So if you want to get the dummy batch, it's going to be something like that. So it's gonna be your next, iter, and then train DL, right? So we already had this line before, so I didn't run that out again. And what we're going to do is that, so you see the Monai version, when it's the Monai transformations, whenever they give you the data set, the data loader, if you have used dictionary transforms, then you need to work with those batches as dictionaries as well. So we have our dummy batch, and you see this dummy batch has some keys. So if you load the image key of this dummy batch, it's going to give you the image. If you load the mask key of this dummy batch, it's going to give you the mask. So it's going to be kind of a dictionary playing here. I'm loading my dummy image, dummy mask, and the reason that I call them dummy is that I'm not using them for any kind of real training, right? And then most importantly are dummy logits. So I'm feeding in the dummy images to my model and receiving some dummy outputs. Now, I intentionally use the word logits here because I wanted you to know that some people refer to the output of a model as logits, specifically the unpreprocessed or the not preprocessed outputs, right? So you might say, why didn't you call them predictions? Because they're really predictions. Yes, they are. But probably you need to pre-process, you need to post-process logits in a way that now they become the predictions, right? So that's the reason that I use the word logits here. And you should also keep using that if you are referring to anything coming out of your model, but before changing that to real predictions. And please note that whenever you are dealing with, PyTorch models, Mooneye models, whatever that are running on GPU, you need to send them to your GPU card. So these two.CUDA, which is also equal to this one, right? You could say that to device equals to CUDA. That's other way for that, right? Both of those work. Now, we have two different devices, CUDA and CPU. Obviously, whenever you say CPU, the models and the tensors are going to be on CPU. And then if you're dealing with GPUs, you need to send them to CUDA, right? And note that my model is also on CUDA. So I sent my model to CUDA, and then I sent my images and masks to CUDA. If one of these is on CUDA, the other is on CPU, the model is not going to run that. You are going to see an error saying that, hey, one of your images, or maybe one of your model or your images is on CPU, the other is on CUDA. Please put them on the same device. And obviously, we always want them to be on CUDA most of the times, unless you do not have a GPU, because CUDA is much faster. So CUDA is the fancy name for NVIDIA graphic cards, right? GPU, CUDA, NVIDIA graphic cards, everything refer to the same stuff. All right, now we got our logits, and please note that this dummy image here, let me run that, and I'm going to print out some shapes for you. First of all, let's take a look at, if I can, oh no, maybe I should add a code cell here. Okay, so if that one works. So here we have the dummy logits.shape. It's 8 by 2, if you saw that. 8 by 2 by 128 by 128. If I point out the shape of the images, they are going to be a little bit different. 8 by 3 by 128 by 128, 8 by 2. So again, these final two values are a resolution. This is the channel. This is the number of images that are batched together using our data loader. And as the prediction, obviously we had 8 images in a batch, so we need to have 8 outputs. So this is a tensor of size 8. And then when you look at that, you have masks, again, as 128 by 128 resolution, but your masks have 2 different channels rather than 3. Why? Because one channel stands for the background, the other stands for the long area. And how do we understand, how do we now post-process these logits to get the final predicted mask? So if you look at this matplotlib subplot here, the first 2 columns we already know about. So this part, we already know how it works, right? We are just visualizing the images, and then you see here that for visualizing we usually bring the stuff back to CPU, and this detach argument here means that, hey, get rid of all the gradients that might be stick to these images from the training. Obviously we did not train anything, so you could have even omitted this part, but it's a good practice to always detach things before bringing them back to CPU, because your GPU might crash if you don't do that. All right, but now look at here. What did I do here? I mean, how did I, so first of all, in the third column, I have my original image. again, as the background image to overlay something on top of that. So I can put also these things here. The thing that is really different is this part. Look at that, right? So I got my logits, which were for this specific part, 2 by 28, 128 by 128. Don't forget that I'm going through a for loop, to see each of my images independently. So again, so if I print out this logit shape here for you, it's gonna be 2 by 128 by 128, right? Now, and I'm going to apply a method called argmax. So it's going to tell the model that, hey, look at these two different channels at each pixel. So each pixel has two different channels. One, the value predicted for the background, the other, the value predicted for the, the long class. And see whichever of these values are larger. So if the value for the long is larger, then you are going to pick the argument or the index of that channel. So we have two different channels, say like that. Channel 0 for the background, channel 1 for the long areas. And each of these two channels have their own values. Now, if the values of channel 1 is higher than the value of channel 0, then this argmax is going to return 1. But if the pixel belonged to background and the value predicted for this channel was larger than the value predicted for the first channel, now the channel 0 has an index 0, so the value that returns is going to be 0. So you see here that if I apply this logic.argmax, now things are going to be different. In fact, things are going to have now one channel, because now instead of having two channels, you have somehow taken care of mixing your two channels with a specific formula in mind. I'm going to only keep that value which is largest. And that's the way that you post-process the logics of a segmented mask, right? So whenever you get an image with, for example, 5 different classes that you want to segment, and you come up with a final image, output image of 5 by 128 by 128, how do you understand which pixel belong to which class? You apply argmax on those 5 channels and convert them to only a single channel image in which the pixel values come from different channels, the ones that we really predicted. They were predicted stronger than others. Now, when you look at here, you see that we have the image, the ground truth segmentation, and the predicted segmentation, which is obviously a mess because the model is not trained so far, right? So look at these segmentations. They make no meaning. But still, if I were you, I would say that why didn't the model simply pick, maybe the entire image as a segmented mask? Maybe why didn't predict everything as background? Why it is like that? It means that no, it is not totally meaningless. It is picking on some edges. It is picking on some angles, things like that. Well, basically, that's the most our images have in common with ImageNet images, with car, and horse and dog and cat images. Only some corners, some edges, things like that. So that's the most that a pre-trained but not fine-tuned model, as Farzan says, can do for us, right? So that's before the train. Now let's quickly go through a couple of other things here before we jump into the training itself. Now, first the loss function, and second the metric. Now, whenever you are putting together a training pipeline, you definitely need to have a loss function. And you already know the loss function. That's the function that penalizes the model during training with gradients and signals the model to be better and better. Now, in classification tasks, you might have already heard about the cross entropy or binary cross entropy and things like that, focal loss, losses that usually you use for training the classifier. Now, for segmentation tasks, we can use the same losses. It's not like that we cannot. But people have understood gradually that if they add a specific loss function to their pipeline and maybe combine that with the regular classification loss functions, they're going to have the best values. Now, the loss function, which is super famous for segmentation, is called dice loss. And dice loss basically penalizes the model if the overlap between the area that the model predicted, say the circle B here, and the area that the ground truth mask had for that class, say circle A, is small. So it's going to penalize the model if this overlap is small. It's going to push the model to increase this overlap area. And if you look at the mathematical representation of that, it's super simple and super easy to understand, right? So What we are going to do is that we are going to take the same formula and use that as our loss function. How do we do that? Again, Mr. Monai comes to help, right? It also has a lot of loss functions, among which the one we are going to use today is called dice cross entropy loss, which basically means it has the cross entropy loss for classification. And you could imagine a segmentation task as a classification task, which is happening at the pixel level, right? For every single pixel, you are going to classify. You also had heard about argmax in your classification course, I bet, right? So basically, this is a similar concept here. But you are not only going to rely on cross entropy. You are relying on an average of cross entropy and dice loss, right? And how do you do that? Monai takes care of that. It has this nice class, dice cross entropy loss. And you need to feed in some arguments here, which are not that much difficult. So one thing that it needs is that it needs you to have your ground truth masks to be one-hot encoded. And what on a one-hot encoded, you might have heard about that if you have already seen a classification model. It's not something fancy. What it means is that, hey, if your mask contains the labels for 4 different classes and your values at the moment are 1, 2, 3, 4, or maybe with the background 5 different classes, 0, 1, 2, 3, 4. Now, if you are going to make it one-hot encoded, it needs to have 5 different channels. So it basically needs you to pre-process your ground truth masks the way that your predicted masks were pre-processed, like to have 1 channel per class of interest. So for example, that example I gave you is going to result in a 5-channel mask. So this one-hot encoded is something that you could do very easily manually, and I think I'm going to do that by myself during the training. But this class here makes things even easier for you. It says that, hey, if you want, I can take care of one-hotting y vector for you. The y is always your ground truth data in the Monai language, right? So y is your ground truth mask. And then it says that, hey, do you want me to apply a softmax on your predicted mask as well? Because that's something that we need before applying the argmax, right? I didn't do that above because we were not training the model. But usually before applying the argmax, you need to apply a softmax function, which easily if you apply a softmax on 2 values, it makes those 2 values to add up to 1. So now you can easily apply argmax and pick the largest value of both, right? So the meaning of softmax, if you apply softmax on 10 values, the softmax is a mathematical function that is going to change the values of those 10 numbers in a way that now they add up to 1, right? So softmax is something that you might have heard from classification. Again, I don't have time to explain everything from the classification background, but feel free to ask questions if you didn't know that. And then when you have your loss function defined, getting the loss is super easy. You just need to feed in your logits, the prediction that the model made, and then your ground truth mask, and then it's going to give you a loss value. Now, obviously, if you didn't want to feed in the softmax layer here, you could set that to false, and you could run the function by yourself. But look at this value here, right? So maybe we needed to first run that cell because that might be a little bit different compared to the last time. Let me run it. All right, so it is 1.20, right? Now let me put it to false and then come here and uncomment this ones. So this is similar to this one, right? Because you set this softmax to false, you manually applied softmax on top of that. Now tell me, do you really expect the value coming out of that to be the same as before? Don't forget, this is 1.20. Now look at that. This is 1.19. Close, but not close enough. Not exactly the same. What happened in the background? Anyone interested to say? What did happen in the background? I'm not going to wait too much for this one because I know this is a little bit more complicated than the previous questions I raised. So just to give you a heads up, guys, when you deal with these Python packages, PyTorch packages, Monai packages, you should always know the things that those commands you use do behind the scenes. Now, let me tell you something. The cross-entropy loss that Monai is using in this loss function comes from PyTorch. And the PyTorch cross-entropy loss, by default, applies the softmax function for you. So when you do this, when you pass the softmax argument to this class in Monai, Monai knows this. So it's only going to apply softmax on your logits before feeding them to the dice loss, not to the CE loss, because it knows that the PyTorch will itself apply the softmax for you. But when you blindly do this by yourself, you are basically, I mean, you are fine with the dice loss because the dice loss in its PyTorch implementation doesn't have cross and softmax. But you are basically applying softmax 2 times for the cross entropy loss. 1 time here and 1 time in the cross entropy loss that the Monai operates from PyTorch, right? So important note, always know what you are doing. So this work here that I just did, this is not the right way for doing that. You need to comment that out and set softmax to true. And if you found things like that in your code, always dig into it and go and understand why things are not exactly the way they should be. If they are not the exact way they should be, probably something is happening behind the scenes that you are not aware of. And believe me, more phila, you are always going to be screwed for that single thing, I promise you. All right, now the loss function was set. The other thing that we usually see in the deep learning task is a metric that we use. I mean, the loss itself could be a metric as well, but people mostly think about other metrics as well. Most of the times, you know, the loss functions have this strong limitation, a strong constraint that they need to be differentiable because we need to get their gradients. But not all metrics that you and I, or maybe the experts in different domains, care about are differentiable, right? Not all mathematical things that they want to do is differentiable. So most of the times people come up with metrics that are not differentiable. Sometimes their metrics are also differentiable. For example, dice, which is the most famous metric for, you know, a segmentation task, is differentiable. And that's the reason that you also see it as a metric and you also see it as a loss. But there are a lot of different metrics that are not differentiable, so they cannot be used for a loss function. And people do their best to estimate them using, you know, differentiable loss functions. But at the same time, they follow their training using those metrics to make sure that the model is actually going through the path they wanted to. So here, just to show you how the metrics could also be defined for a segmentation task, I'm sticking to the dice metric, again imported from Monai. There is only one huge difference here. The dice metric doesn't one-hot encode your ground truth mask, so it doesn't have this argument, and it also doesn't have these arguments. So you need to take care of those manually, and that's something that I don't like about Monai. They basically can make things a little bit cleaner instead of just adding more and more features. But you know, I am not in their team, so I cannot tell them what to do and what not to do. Anyways, so we have this dice metric defined, but we cannot easily feed our own masks and predictions there. We need to do a lot of handy things ourselves. You know, if you want to one-hot encode things, it's very simple. Again, thanks to Monai itself, you just say, hey, this is my mask. I'm going to one-hot that. I need to have my input mask. This is our ground truth mask. And I'm going to one-hot to 2 classes because, you know, this command here needs you to determine the number of classes your mask is going to be one-hot encoded to. And for our case, we only had 2 different classes, so we need 2 different channels as the output. So let's one-hot encode that to 2 different classes. And then for the prediction, what we are going to do is that we need to first apply the softmax function on the logits. And that was the reason that we didn't call them predictions, because they needed some sort of post-processing. First, apply the softmax, name them dummy pred, then bring them here, get the argmax out of them, change them back to float values. And then finally, maybe I should have put an inter here. Oh, no. Change them to one-hot encoded as well, because your dummy prediction also needs to be one-hot encoded. So again, the same command here. So we one-hot encoded both our mask, ground truth mask, and then the predicted mask. Obviously, the predicted mask was one-hot encoded after the softmax and argmax application. Now that you have taken care of those, you could basically run your metric function on top of these 2 for your prediction and then for your ground truth mask and get your metric. Now, someone please tell me, what happened that we had only 1 value for the loss as we fed in a batch of our data? And now we have 8 values, better to say 8 lists, and each list has 2 values as the metric, because we apparently applied the same things here, dice on dice. Why did one give us one single value and the others gave us 8 lists, and each list contains 2 different values? Anyone interested in sharing their opinions? Anyone interested to guess? Don't be afraid, just say something. Nothing will happen. Is the metric for each image in the batch? Yes, you're right, Anna. Yeah, the metric you're seeing in the batch belongs to every image. And I can give you a little bit of hint here. Let me make it a little bit easier for you. So you are seeing 2 metrics for each image. For example, for image 1 in the batch, for image 2 in the batch, image 3 in the batch. And you're seeing 2 different values for each image because dice is calculated per class of segmentation. So you are seeing one dice value for background, the other dice value for the long image. One dice value for background, the other dice value for the long image. Or maybe vice versa. Probably this one is for background, this one is for the long image because the background class is 0, right? But here is the chess. And I promise you the same thing should have happened for the loss as well. But why do we get one single value for the loss? What is happening behind the scenes? Because we definitely had something similar for the loss as well. How did we change a tensor like this to a single value like that? Proudyville says no stress. Thank you. Yeah, probably that's the right term. Anything else? So the thing that happened there is that we get the mean or the average of all of these. Don't forget that the loss is going to be used during training, guys, right? During training. So what we need is that we need to have our values. I mean, just see it like that. We have one loss value per class per image. So 2 loss values per image, one for the background class, the other for the long class. And then 2 values, for each image, so 16 values in total for a batch of size 8. Now, but this is not going necessarily to help us, right? We need to simplify that into a single value that now we can get the gradients on. And the way that we do it is that we get the average of all of these. So the average of the background class loss and the long class loss across all the images. And when we get those 2 values, one loss value for the entire background, the other loss value for all the long images across all the images, we even get the mean of these 2 values. And finally get one single value here, which is the loss in that single batch, right? Now, you might ask yourself, can't we weight that in averaging? Can't we, for example, tell the model that, hey, we care more about the weight, the loss of the long areas rather than the loss of the background? Obviously, you could do, and I know that if the dice cross-entropy loss should have a weighting argument for you as well that makes the averaging a little bit weighted compared to a normal averaging. So that's something for you to go and figure out and play with, but you definitely can, play with that, specifically if one of your classes is very small, maybe not as large as the entire lungs, but maybe say we were caring about segmenting one specific vertebra on that radiograph, right? One vertebra on that radiograph, maybe vertebra number 5, for example, cervical vertebra number 5. That would be a very small area. So the model had a huge background class and a very small vertebra area. On that case, you probably wanted to weight the model weighted model more towards the loss for the vertebra class, because the vertebra class was very small. The model might actually miss that because the background class basically gave it the best results, but you want to push the model towards the smaller class. But here in our case, we don't need that because we basically have our model in a pretty much good shape. All right, any questions so far? Marlene said, is this due to the loss function? Yes, you were right. That was because of the averaging in the loss function. Thank you, Marlene. Any other question or comment? Shall we proceed? All right. Happy to see that people have stayed. Didn't expect that. Now the training. I'm not going to spend too much time on it because you probably know it from your previous sessions and things are not that much different. You need to define some hyperparameters here. Obviously, we need to define the number of epochs, the number of times our model is going to see our entire data set, our learning rate. This is a try and error game. Sometimes you could play with learning rate schedulers or learning rate optimizers that you could understand what learning rate works better for you. But in our case, learning rate of 1e-4, which is, by the way, if you are not familiar with that, equal to this. So this is 1e-4. If I put one more 0 before the 1, that could be 1e-5. If I change it like that, that would be 1e-3. So be careful. If that would like that, that would be 2e-3. So learn this notation. This is going to be helpful for you. But anyway, so let's correct this here for now. And then, so the optimizer is going to be Adam W, which is one of the nice optimizers. So just a quick recap, optimizer is a Pythonish object programmed in PyTorch that helps you to go through your loss values and make sure your model parameters are changed in a way that your loss becomes smaller in the next cycle, right? So that's optimizer. Batch size, now we redefine our train and test data loaders here because now we're going through a real training rather than a dummy one. I set the batch size to 16. That works fine. On my Colab Pro here, you might need to bring it down to 4. And also, as I mentioned before, you might also need to resize your images to a smaller resolutions than 128. So if you just notice that the entire notebook died, go back and rerun the notebook. You probably won't have to wait too long and then just play with this batch size. I recommend you not to play with the training at this moment because I already have the weights of a retrained model for you. Then if you don't train your model, you probably are going to be fine for the next cell. So just let me go through this part on my own here. But if you want to play with that, just be careful that the Colab Pro or Colab Basic might be different with respect to running these things. Now, coming back to the training, the main training cell, this is the longest cell in my notebook, but it is super simple. So we have an epoch loop in which we go through different epochs. So this for loop is going to be run for 5 different times. And then each epoch loop contains a training loop and a validation loop or a test loop, right? And then finally, there is some logging that happens at the end of each epoch. And if the model is a good model, we save the model. So that's the big picture of this cell. Now let's break it up. The first thing that we do is that we define some empty list to log the values that we would like to visualize after the training. We usually care about the loss values for the training and validation. And at the same time, one of the metrics or a couple of the metrics we define, like dice, for example, here. So what we do is that we start the training, we print out the number of epoch we are in, and then we go. So let me run this because I'm going to explain, and this may take time. And at the same time, I'm going to explain to you as well. It seems that we didn't define our metrics. So let's go back here. Oh, this was run. Maybe here. We should find that one. And then rerun this. So hopefully it goes, oh yeah. Now you see starting epoch 1 out of 5. Don't forget that this is epoch number 1 and we were playing with the persistent data set. So epoch 1 is going to be the longest here, right? So it is training. You see this fancy progress bar coming out of the TQDM package that you could see here, and playing with that is very easy if you just want to go and check the documentation of that one. And we are sending each batch into training. So every time that this progress bar goes forward, one new batch is introduced to the model. For each batch, we get the image and mask out, zero grad, the optimizer, as you probably know from before, send the image to the model, get the logic out, send the logics and the mask to the loss function, get the loss value out, call backward on the loss, and finally optimize the step. So these two lines take care of getting the gradients out of the loss, and then finally making the models better, to making the parameter of the models to improve and improve over time. And then we append the value for this specific, the loss value for this specific batch to epoch training loss. So this epoch training loss is the same empty list that is defined at the beginning of every loop. The way that I am logging here, which might not be the best way, honestly, but this is a dirty way for doing that. I am logging the loss values at every batch, appending them to an empty list that is defined in the beginning of every epoch. And at the end of that epoch, I am going to get the mean of all those values for all batches in that epoch, and then append that here, append that to the main list that I defined in the very beginning, which actually included the log values for the entire epochs, right? So I'm somehow logging on the epoch level. And then for doing that, I need to log on the step level as well, on the batch level as well, and then just playing with the values a little bit. This is not the best way. Honestly speaking, in the real world, we usually deal with software like WMB or TensorBoard, which take care of the logging stuff for us. So we never log things like that ourselves unless we need to. So this is only for the sake of keeping things limited to this notebook. So the validation we were here, we basically logged the loss, and then we needed to have the metric as well. And don't forget that for the sake of the metrics, we needed to apply the softmax, argmax, and then one hot encoding for the ground truth mask and the logic predicted by ourselves. And then finally feed things through the dice metric function, get the dice metric out, get the mean out of that. Why did we get the mean? Because don't forget that the output of the dice metric is going to be something like that. This is not something that we could log. We need to get the mean out of that, and we log that out, and then finally add it to epoch training dice metrics as well. Now, things are pretty much similar for the validation loop as well, and at the same time, please also note, we missed a few epochs here, but please note how things got much faster. Now look at this validation loop and also the training. It's going much faster compared to the training because now it's a persistent data set. Now, looking at the validation set here, what we are seeing is that things are pretty much similar. The only difference is that, for training, we put the PyTorch model in the training mode. For validation, we put it in eval mode. For those of you who are more familiar with PyTorch, what this change behind the scene is that, for example, if your model is relying on some dropout nodes for kind of regularization, the dropout nodes are going to be turned on for training and turned off for validation. If you are not familiar with such concepts, just ignore that. This is a take-home message. Put model.train before the training loop, model.eval, whenever you are going to apply your model for inference, including the validation loop. Now, things are going to be, again, pretty much similar. The only difference is that we have a with clause here that has with torch.noGrad. This basically is telling the model that, hey, be careful. There is not going to be any learning happening here. No gradient at all. This is only for the sake of validation, only for the sake of understanding if our model is doing a good job or not. How do we do that? We put torch.noGrad, and then we apply our model beneath this class so that now we are sure that PyTorch behind the scene is making sure no gradient is calculated for our model, right? So we go like that. And now, again, the logging stuff, similar to the training part, and this final part, which is important. So you train your model, but if you don't save it, you probably are going to regret training that at all, right? Because you basically have not saved the model for further use cases. How do we save that? So the way that people usually save their model is that they save it at the end of every epoch based on some criteria. The criteria that I usually work with and most people usually work with is called the best validation loss. And the best validation loss is actually the lowest value for your validation loss, the one that you usually care the most about, right? So don't forget that during the training, we expect the training and validation loss to decrease and decrease and decrease, right? So sometimes the validation loss might stop decreasing, denoting overfitting, or in simpler words, denoting that your model is not learning anything after that, right? So you basically you want the weights of the model to be saved from the checkpoint in which the model had the least validation loss values. Now, this is not necessarily the last epoch of your training. So for example, you might train your model for 100 epoch, but your model might have stopped learning after epoch number 20. So you should probably have a way to save your weights at epoch number 20, right? And the way that we usually do that is that we define a simple float variable called best validation loss and define it to none. And at the end of each epoch, do something. We say, hey, if best validation loss is none, which basically means we are in epoch 1, there is no better alternative available, or if the epoch validation loss, means the epoch validation loss at the current epoch, is lower than the best validation loss that you ever have seen, maybe from the previous epochs. Now proceed to saving the model. Set best validation loss equal to the new loss that you just got. Create a folder for the weights, and then use torch.save and save the parameters of your model, right, to a path. And if you look at here, weights, this best model.pth has actually been saved here. If you did not run your training, you might still see it here because I already put it in the GitHub repository, so that if some of you could not run the training, you could still play with the trained model. And the model also gives us a point that, hey, I found the best model, hooray, and everybody's happy, right? And things get going on. Make sure to be a little bit obsessive with your training code. Don't be dirty in coding. Coding cleanly is very, very important, probably as important as training and curating your data, right? So make things look really beautiful, honestly speaking. And this is 50% beautiful in my mind, but anyway. All right, now you do that, and your model is saved. And see here that our model was basically saving best weights every single epoch we had. This means that your model had still rooms for improvement. So basically, I might need to retrain their model with maybe 10 epochs instead of 5. But for the sake of our task, that's totally fine. All right, now we trained our model. And I'm going to proceed to the final part, which is evaluation. But before that, let me see if people had any questions regarding the training. Farzan, there is an important difference here. If the model considers a pixel from the background instead of the long, then the probability that it considers pixel from the long instead of the background. How should we fix the problem? Very cool question and very good question. Thank you, Farzan. The way that you need to fix that is by weighting your loss. So the way that we penalize the model to consider some tasks more important than the others is by weighting the loss or by increasing the data points. Now, increasing the data, for example, oversampling the data, works fine if you are dealing with a classification problem. Say if you are classifying people with normal radiographs from people with radiographs which contain pneumonia pathologies, right? In that case, if it is a classifier deep learning model, you might oversample your patients from the pneumonia class. Say you had 2,000 patients, only 100 of those had pneumonia. So this is a very imbalanced data set. You oversample the number of patients in your pneumonia class. You basically duplicate using heavy augmentation the radiographs which belong to the pneumonia class. This is not as valuable as the situation in which you had more real pneumonia classes, more real pneumonia radiographs, but it still is going to be better than just training the model on pneumonia classes. Now in segmentation, oversampling is not very easy because imbalanced data patterns are seen within a single radiograph. So if you just duplicate a radiograph, that imbalance pattern is gonna be duplicated as well, right? So what you do and what is easier to do to deal with imbalance problem in a segmentation project is by weighting the loss function. So didn't I tell you that you could weight the loss function, make, for example, a dice loss for different channels? In other words, for different classes, you weight it more towards, for example, that class of interest, the long class that you are interested. So you make your model think that, hey, if I miss one background pixel is less important than if I miss one long pixel. I'm not going to miss that one. So that's the way that you need to play with your loss values. Thank you. That was a very good question. Now, the evaluation. We have only 2 or 3 more cells to run, guys. Good news. And let's see what happens here. So obviously, we logged everything here for the sake of visualizing them after the performance and looking at them. So let's do that. Now, if you come here, let me run it one more time. So this is for the current training. We have 2 different plots here, one for the loss, one for the dice, our metric. Blue indicates the training. Orange indicates the validation. And as you can see here, both our training and validation loss had decreased very nicely, very cleanly. During the training, it seems that it's almost plateau, maybe it needed 1 or 2 more epochs, but it's almost plateau. And then for the dice, also the same. You see that the dice values are increasing, and they are basically pretty much close to 0.96, 97, which basically means that 96, 97% of our masks have overlap with the ground truth masks. Now, you might wonder why the loss for the validation loss is lower than the training. This usually is the reverse in the real projects here. The reason is that our task was very easy. and we overkilled with the number of augmentations we applied to the training data. We actually made our training arbitrarily more difficult than was necessary, right? We even made it more difficult than the validation task. So that's because of that. Sometimes it happens during the real training. It's not a bad thing. It's not something that you need to fix. I have had real projects that we published, and the training loss or the metric loss was like that. It's not a bad thing at all. So, but if you're just curious to know, if you have heard that, hey, training loss needed to be always lower than the validation loss because the model should have a difficult job on the validation, that's true. But sometimes you might overkill and make your training even more difficult than your validation. That's the case here. So that was the answer to this question that I put there. I tended to answer myself, not to take more of your time. Now let's do something fun. Finally, we have our model. We trained that. We have saved the weights. Let's proceed and see how the results of that model should look like, right? So imagine that we didn't have this notebook and things were not running as it is now, right? So we needed to reload our model from scratch. Note here that I don't need the pre-trained weights anymore because now I have trained the model by myself. I'm going to load the weights that I myself have rather than train the ImageNet weights. I don't care about that one anymore. I define my model, and then I call load state dict command or method from a PyTorch model. Don't forget that Monai is written on top of PyTorch, so whatever Monai object you have, they are also PyTorch objects. So you just call load.stateDict command from Monai, and you give the path of the weights that you saved, and you bring it to CUDA. As I mentioned before, whenever you are not training your model, you put it in the evaluation mode. Run that. It's going to run very easily. And then finally here, let's do that. We are going to have a batch of our test data loader. So don't forget, this is a batch of our data that our model was not trained on. And we did our best to make sure that the model is not cheating with respect to splitting the data, right? No patients that the model is going to see now had been seen in the training. We get a batch out of that, images, masks, logits, like that. And then let's do something nice, right? Let's put it there. Let's put it in the for loop, print it back here. And one thing I probably forgot to put here, but the models are still doing a good job, is that I might also need to apply the softmax here as well. Let's see. Logits, torch.softmax. Logits again. Equal to 1.argmax. So I mean, you could do a better job rather than making things this much complicated here. Things could go to different lines. I just did the simple things here. So this is very similar to the previous pipeline we had. Now I apply the softmax and then I apply the argmax. This might need to be dimension 0 like this one. I'll see what happens. All right, let's go. Let's run these and wait for the final results. Here we go. Now, on the middle column, you're seeing our ground truth segmentation. On the right-hand column, you're seeing our predicted segmentation, the one that we just got from our models. Look at that, the image, the ground truth, the predicted segmentation. It's doing a pretty good job, right? I mean, most of the time, it's segmenting where it should be. Now, there are some nuances, there are some differences here that you might notice. For example, look at here. You see this sharp edge of the left line, bottom edge of the edge line. So this corner of the line, it seems that the segmented model has not learned to pick that up. Now, why is that the case? Maybe because there was an inconsistency on our ground truth data. Maybe some annotators picked that in their manual masks and some didn't, and the model did not learn that. Maybe because we needed to keep training our model for longer so that it can also learn these nuances, right? But most of the time, it's doing a good job. Look at here. I mean, it's not doing a bad job at all. It has learned to ignore the other lucencies on the screen. It has learned to basically get the most out. Again, as you can see here, it has not gone as deep as the ground truth mask on this corner. In my opinion, it's good. It's doing a reasonable job. And it has a good performance on both large and small lines as well, though the diversity is not very clear here. But for example, look at this one. You see this? Guys, this is a very good example. That's the reason that we put augmentations in our training data. These patients, look at the spine here, right? Do you see the vertebral column? Do you see this kind of curve here? This is not natural compared to other patients here. So this patient has Scoliosis. This is a pathologic condition in which the patient's vertebral column basically rotates pathologically, and these patients unfortunately have a lot of problems in their musculoskeletal and also in other systems, including the respiratory system, because of this kind of pressure that you see here. Now the vertebral column is putting towards the right lung here. So these patients cannot lie down naturally on a bed when they are going through a radiography. They need to lie like that. And now what happens is that when they capture a radiograph, part of the right lung is not quite visible on the radiograph, as you see here. Now, the model still needs to, we need our model to be robust. Those models should still be able to segment the lungs here, right? Now, the reason that the model learned this at all, I mean, in general, was because of all those arbitrarily kind of augmentations that we put into the training pipeline. We forced our model to look at weird situations and still have a good performance. And that's the reason that at least the model has not missed any part of that. But look at here, compare these two masks with each other. Do you see that this mask is actually a little bit sharper with respect to the border, internal border of the right lung? And look at this one. This has actually captured a part of the spinal column as the area of the lung, which we really do not like it to. So it needs more training. I mean, if I look at these results, I would definitely say let the model be trained a little bit more. If the problem persisted, then I need to go back to my data and make sure I have enough representative cases like that in my training, or maybe like all my annotations are actually consistent with respect to the segmentations, manual segmentations on these corners. A lot of times, guys, this happens that you come, you train a model, you look at the model performance after a lot of weeks, and you see that, hey, there is something there that you didn't notice, even though you did a lot of EDA. And then you need to go back, sometimes even re-annotate your data, correct your annotations, and then come back, obviously faster, because now you have the entire pipeline ready. But deep learning is not a linear process. It's kind of a circular process. You need to go back a lot. Change your data, come back again, train your model. Look at the results, go back. Change your data, come back again, train your model, go back. This happens a lot, so be careful with that. However, now, as a final cell, before I stop sharing the screen and listen to your questions, one of the reasons that people might train segmentation models, specifically in medicine, is to use them out for feature engineering to help another model down the road. What do I mean? Say, I actually did that. I mean, it was the COVID era, the very first months of the COVID. We really wanted to have deep learning models that could look at lungs and understand, I mean, to look at chest X-ray like this one and say if the patient has COVID-19 or not, or maybe if the patient is definitely a COVID-19 case, is he or she going to live long or not? What is the prognosis? Things like that. Now, for that, we definitely wanted the model to take a look at the lungs, right? So one of the things that we did was that we thought maybe the model will have the classifier model. So we were going to train a classifier. Is the patient a COVID-19 or not, right? And we did not have too many data points. Our data sets were small. It was the beginning of COVID, not too many data sets were available. We had very few patients at Mayo on that time, and we only had a few cases to look at. So we thought probably we need to help that classifier model a little bit by removing out the irrelevant part, or at least the less relevant part of the image, and let it focus only on those areas of the model that make the most sense for the final classification. So what we did was that we trained a segmentation model like the one that we just trained together, and used that out to crop the entire image and only keep the long areas. What do I mean? I mean something like that. Look at the code here. The code here is super simple. And cropping is done easily using torch.var or numpy.var. And I'm just saying that, hey, apply the argmax, right? And only keep those pixel values which were 1. If there are pixels for which the argmax is returning 0, it means that they belong to background and I don't care about them. For that, those pixels, remove them and replace them with the 0 pixels. And then only keep the image pixels which belong to the lungs. And now look at these images, guys. These are cropped lung images. And we trained our down the road classifier on these kind of images. And it was much better than training that the first version we trained on the original images. This kind of concept that I just introduced to you is called feature engineering. It means that you sometimes help your model by modifying the features or the attributes of your input data to that model a little bit. And sometimes feature engineering itself is done using another deep learning model. So one of the main use cases of segmentation models is to be used as cropping tool for further feature engineering for a downstream model. And that's the way that we did that on that time. That actually brings me to the end of this notebook. Sorry that it took probably 1 hour longer, but as you said that you were probably fine with the going over time. I did my best not to rush through any details. Hopefully that was useful to you. Sorry if it was boring, too much long.
Oh, no.
Like,
don't apologize. I really enjoyed it, especially the last part where we talk about the feature engineering, where you use one deep learning model just for the purpose of feature engineering for downstream task, and that's especially important when we have a huge amount of data. I've seen research done specifically on that. It's a really cool trick that that when you have such a large amount of data, you just want to crop to specifically the bounding box that you especially want to work on, and using a deep learning model to on top of like a simple not simple UNet, in this case you use an efficient UNet to crop on your region of interest to go forward to the next task is really a smart idea. Did you do this in your own project, in your own research? Or
yeah, I mean, on those days we did use that. I mean, so probably you remember, I mean, the deep learning word was actually filled up. I mean, like the other areas of research. I mean, everybody was working on COVID. Everybody was publishing COVID. Journals had a very low interest, bar for accepting COVID papers. So we were also working on a couple of those projects. We never ended up publishing that one because we basically wanted to use that at Mayo, and we did for a period of time. And then after that, another team came up and they had another data sets from another country. So we mixed the merged data sets. But yes, I mean, so this is the thing that, and I also remember that we once did that for a Kaggle competition, and it helped us to go up through the ladder for a couple of ranks. So yeah, this helps a lot. I mean, feature engineering is a concept that a lot of time makes work. But there is something there that, I mean, you should always have the performance of your model with and without feature engineering and compare it. Because, one nice insight on those days Brad had, and we were quite curious about that. Unfortunately, we couldn't test that out in a very rigorous manner because we didn't have the data. But that, hey, how do you know that the model cannot realize if a patient has COVID-19 by looking at other areas rather than the lungs? For example, the heart. For example, maybe the other things. Obviously, I mean, there were assumptions that we wanted to test out, but maybe he was right? Feature engineering could help or could not help. So that's something that you should always try. Always that if you are thinking of on feature engineering, have a baseline performance and then apply feature engineering, check the performance again. Sometimes it goes down. So you need to redo your feature engineering and stick with your original data.
Yeah, thank you. I see we have one follow-up question by Farzan. Thanks. In the case that we have little data, can we use one-shot learning, or are these models useful in medical problems?
No, they definitely are useful, Farzan. I personally have zero experience with few-shot and one-shot learning models, except for one or two occasional things that I did on my own. But honestly, I'm not a good person to talk about the kind of things that you could do or you could not do with that. But at least relying on the kind of papers I have read and things that I have gone through to review, people are definitely doing that. Yes, you can do that, but don't expect those models to do miracles for you. I mean, those are going to have a reasonable performance with respect to the number of data points you train them on.
Yeah, thank you very much. Farhad, is there anything else you'd like to add?
Yeah, first of all, thank you, Pouria, for the great presentation. I really enjoyed it. Yeah, I really want to emphasize on the point that you made, that understanding data is the key. And unfortunately, that's usually the most missed parts. It's easy to fall in this trap that I get some code, I run it on this data and predict a number. But understanding the data and facing this scenario that any choice that you made in data cleaning and data pre-processing has an effect on improving the performance of model, or vice versa, is very important. Thank you so much. I think that was very good point.
Yeah,
That was all my pleasure. Yes,
yeah,
please.
thank you
Sorry.
very much. And I also agree with both of you that data cleaning, sometimes maybe the most time consuming part is very, very necessary. And I think it's very good that you spent a large amount of time in this notebook to talk about this. And the following parts of the workshop, you also kind of tied up a lot of the previous workshops that we talked about, especially the last one was transfer learning. So it's good that we had the pre-trained efficient with Monai going on there. Yeah, so thank you so much again. And for the rest of our remaining members that are still here, thank you for staying. We'll see you tomorrow. It's the last closing ceremony, and we'll talk to you more about the logistics of the next research phase.
Awesome. Thank you very much. And I would also like to thank you, all these amazing people who are putting thank you points in the chat. Thank you very much. I should thank you for staying with us. And that was quite a pleasure. And then as the final point, Farhad and Eugene, is that possible that I have maybe 30 seconds of words with you guys after the folks left?
Yeah, absolutely.
Ask something.
Yeah.
Thank you, everyone.
Thank you.
Thank you, guys. Bye.
Yeah.
Awesome. So I just wanted to ask you if
we can stop
okay.
the recording for a second, I think.
Oh, sure, sure.
Yeah.